Hello, hello, hello. ইউটিউবও হয়ে গেছে। ইউটিউবে এটা দেখা যাবে। ওই ইউটিউব চলতেছে, ওইটা ইউটিউব চলতেছে, এটা চালু রেখেছি, তাহলে এটা দেখা যাবে। যখন জয়েন করবে তখন ওই পেজটা শেয়ার করে দিব। চলো এই পেজটা শেয়ার করে দিব, তখন ওটা দেখা যাবে। সবার থেকে হবে না, সব মাইক বন্ধ করে ছাত্র সবাইকে ইউটিউব সব ছাত্রকেই পাঠানো, যতজন অ্যাপ্লাই করছিল সবাইকে।
হ্যালো বিভাস।
হ্যাঁ স্যার।
শোনা যাচ্ছে?
হ্যাঁ স্যার।
এত শব্দ কিসে?
ও স্যার, নয়েজ পাশেরটা চালানো তো ওর জন্য।
হ্যাঁ স্যার।
ওকে ওকে ফাইন। একটা বিভৎস শব্দ হচ্ছে কিন্তু।
হ্যাঁ হ্যাঁ। না, ওটা ক্যামেরা অন করলে কোনো ইস্যু হয়ে যাবে। এটা তো হবে না।
হ্যালো ডিনসের।
Everyone, good afternoon to all of you.
ইয়েস, গুড আফটারনুন। আপনাদের কি ওই ইসি শেষ হয়ে গেছে?
হ্যাঁ
স্যার
হ্যাঁ
এখন শোনা যাচ্ছে স্যার?
হ্যাঁ হ্যাঁ, আমি তো
হ্যাঁ,
শুনতে পাচ্ছি।
শোনা যাচ্ছে
এখন
শোনা যাচ্ছে।
নয়েজটা হচ্ছে?
নো নো।
ঠিক আছে। আমি স্যারকে দেখি। আমি স্যারকে দেখলাম। তোর এখানে দেখ।
শেষ হয়ে গেছে?
হ্যাঁ। ইউটিউব ইউটিউব থেকে অফ করে দিই। ওকে।
ও আচ্ছা, ঠিক আছে, একটু থাকো।
শেষ হয়ে গেছে? হ্যাঁ।
ইউটিউবে কজন পার্টিসিপেন্ট? 5 জন। আর এখানে?
স্যার,
হ্যাঁ
ওই মিটিং শেষ হয়ে গেছে তো?
হ্যাঁ হ্যাঁ হ্যাঁ,
আচ্ছা, ঠিক আছে।
শেষ হয়েছে।
আচ্ছা
ওই 1:30 পৌনে 2 নাগাদ শেষ হয়েছে।
আচ্ছা, ঠিক আছে।
ঠিক আছে, হ্যাঁ হ্যাঁ।
এখানে কজন? 22 জন। তো
Good afternoon, sir. Good afternoon, sir.
Good afternoon. Good afternoon.
আমরা শুরু করব এক মিনিট।
Sure. Koro.
Good afternoon to everybody. Our esteemed guest and patron, Honorable Professor Dr. Subiresh Bhattacharya, Honorable Vice Chancellor of our university, respected Professor Pranav Ghosh, Registrar, Acting, and Chemist, Professor S.C. Rai, Dean, Faculty of Science, North Bengal University, Head, Department of Physics, North Bengal University, faculties of the universities and colleagues, and I also see faculties from other universities, research scholars, my dear students. I welcome you all from the core of my heart to participate in the online program. Now we have a schedule welcome address by Dr. P. Mali, Head of the Department of Physics, then welcome address by Coordinator ICARD, then inaugural address by Honorable Vice Chancellor, address by Dean of Science, address by Registrar. So I request Dr. P. Mali, Head of the Department, to deliver welcome address.
Thank you, Dr. Pal. Very good afternoon to all of you. And Honorable Vice Chancellor, Sir, Professor Subiresh Bhattacharya, the Dean, Faculty of Sciences, Professor Subhash Rai, the Coordinator of the ICARD, Professor B.C. Paul, and the Registrar of North Bengal University, Professor Pranav Ghosh, all the eminent speakers, scholars, scientists, students, participants of this program. On behalf of the Department of Physics, North Bengal University, I welcome you all in this international seminar on astrophysics and cosmology. I must acknowledge that even during this ongoing pandemic period that extended over a period of 2 years almost, the ICARD of the Department of Physics, NBU, under the leadership of Professor B.C. Paul, could retain the research activities in its best possible state, I can say. This program is a supporting example of this fact, and I'm quite sure that you all, particularly the young researcher, shall enjoy the program, and they will enjoy the presence of the eminent speakers and researchers attending this event. I'm quite optimistic, you can say, and ambitious that the next seminar of ICARD and any other scientific event of the Department of Physics shall be organized in offline mode. And I thank you all and wishes all the best, all the very best for the seminar. Thank you, all of you. Thank you,
Thank
sir.
you. Thank you, Dr. Mali. It is now my turn as a coordinator. It is my pleasure to organize a one-day international seminar on astrophysics and cosmology at ICARD Physics Department, North Bengal University, which will benefit not only research scholars and faculties in theoretical physics, but the students in shaping their future. Students, basically college students as well as the university students. ICARD is organizing seminars at least once in a year as an activity of the center. We have organized national seminar during pandemic phase, as HOD mentioned. At the end of the COVID-19 pandemic phase, I hope that this will be the last seminar. You will agree with me at ICARD NBU so that we can organize in future in other mode. So there was no financial support required to organize the program, but infrastructure support is required, for which I approached the university authority time to time. For making it a grand success, our Honorable Vice Chancellor, Sir, encouraged us to go ahead. The research scholars of the department took initiative to carry out the most difficult tasks in organizing this seminar with me. Particularly, I should mention Mr. Sagar De and Anirban Saha. Anirban Chando. I have learned from the organization of today's program that it is not an easy task to organize such academic activity in the department. Mr. Anirban Bishwas, head of Center for Information and Resource Management, NBU, helped us a lot in organizing the seminar with internet facilities and Google as well as YouTube platform. Though the department is very new, 2020, it is substituted in our university under the here. The speakers of the day, Professor Mark Trodden from USA, Professor Dipankar Bhattacharya, and others from Russia as well as South Africa accepted our invitation, for which I am grateful. There was overwhelming responses from all over these. We arranged some in the Google Meet and others in the live YouTube streaming. Almost 200 participants requests we have received, and that's why we have made two simultaneous arrangements. Thank you all. I now request our Honorable Vice Chancellor, Sir, inaugurate this program.
Good afternoon, everybody, wherever you are. Respected of the Department of Physics, Professor Mali, the coordinator of the center, ICARD, Professor Bikash Chandra Pal, Dean of Science, North Bengal University, Professor Subhash Chandra Roy, other faculty members, respected faculty members, revered speakers from all over the country and also within the country, dear research scholars, students. The Inter-University Center for Astronomy and Astrophysics, IUCA, in short, is an autonomous institute set up by the UGC University Grants Commission to promote the nucleation and growth of active groups in astronomy and astrophysics at Indian universities. IUCA set up 6 reference centers in India which provided basic facilities to universities or college teachers and students in different regions for working in projects related to astronomy and astrophysics. IRC at North Bengal University is one such center, started functioning from July 31st, 1999, under the guidance of Dr. S. Mukherjee, retired professor, Department of Physics. The center is now renamed as ICAD, the Center for Astronomy Research and Development. Professor Bikash Chandra Pal is looking after the center as coordinator. The center is organizing seminars from time to time, even during pandemic period. The seminar on astrophysics and cosmology is the first one-day international webinar organized by the ICAD with speakers from USA, South Africa, UFA, and India. I came to know from Dr. Paul that there are 192, almost 200 participants from different universities, colleges, and institutes across the country, South Africa, Russia, and Malaysia. Among these 192 participants, some motivated BSc and MSc students from different universities and colleges are also there. In addition to that, the center has also made arrangement for accommodating large number of participants via Google Meet as well as YouTube streaming platform. I welcome all of them to this webinar. We know that astrophysics and cosmology involve the study of the physical processes that govern the behavior of astronomical objects and the study of the origin, evolution, composition, and the fate of the universe as a whole. Many of the most vexing and fundamental unsolved problems in physics are being tackled by it. Astrophysics is fundamentally astronomical, while cosmology combines astronomical knowledge of our solar system, our galaxy, while cosmology combines astronomical knowledge of our solar system, our galaxy, and our universe with philosophy. Cosmology is probably the most ancient body of knowledge, dating from as far back as the predictions of seasons by early civilizations. Yet until recently, we could only answer to some of its more basic questions with an order of magnitude estimate. This poor state of affairs has dramatically changed in the last few years. We are entering a precision era in cosmology, and soon most of our observables will be measured. We are truly living in the golden age of cosmology. Important results are coming out almost every month from a large set of experiments, which provides crucial information about the universe origin and evolution. I will not say much on the topic because there are a number of resource persons. They will highlight the topic, and I am sure the participants, both from the research scholar and the students front, will be immensely benefited by the deliberation made by the resource person. I declare the webinar open, and I also wish this webinar a grand success. Thank you very much.
Thank you, sir. Thank you. Thank you, sir. With your permission, we move to address to be delivered by Dean, Faculty of Science, North Bengal University, Professor Subhash Chandra Rai. Please.
Okay. Thank you, Professor Pal. So, at the outset, I must convey my sincere thanks and gratitude to our Honorable Vice Chancellor Dr. Subiresh Bhattacharya for giving the permissions and granting the processes to hold that kinds of international seminar on astrophysics and cosmology today on 3rd March from 4 to 9 p.m. And also I am thankful to BC Pal, Professor BC Pal, coordinator, for arranging this nice international seminar on that astrophysics and cosmology. I am thankful to HOD, Dr. Prabhas Mali, that he has arranged nicely to conduct the seminar in collaborations with the Professor B.C. Pal, coordinator, ICART. So I am thankful to all of you. Now, on behalf of the Dean, Faculty of Science, I welcome all of you, those who are eminent scientists from various countries along our from Indian sides, all the scholars, students from abroad or our country or our university in this national seminar or webinar on the international astrophysics and cosmology. So I hope that students will be benefited from the deliberations by the eminent scientists from Russia, then Brazil, then some other places, and from our Indian scientists also delivering their speech on the topic of astrophysics and cosmology. So we know that cosmology is a very old one. We are not accustomed with that one because we are from botany side. So I will not say anything about the topics, but I congratulate to BC Pal for organizing such new topics and advanced topics of the astrophysics and cosmology. So with these few words, I convey that this will be grand success. I hope that all will be benefited. Thank you all.
Thank you. I now request Registrar Professor Pranab Ghosh. I think Pranab Babu, he may be in some.
I think he is busy with some other job. No?
Yes, then we want to conclude here. We will go next to our invited talk to be started at 4:20. And the chairman of the seminar is Professor M. Bharma, Murli Manohar Bharma from Lucknow University. So until 4:20, that means 4-5-7 minutes, we just wait. I think Professor Bharma.
Okay, yeah.
I think just
Hello.
1 minute. Professor Konok Saha is already present. So
Right.
up to you.
Oh, all right. So I'm happy to be the part of this webinar, International Seminar on Astrophysics and Cosmology, organized by the IUCA Center for Astronomy Research and Development, ICARD, Physics Department at the University of North Bengal. I'm thankful to Professor B.C. Paul to have asked me to chair the session. This will be having two talks in a row. The first talk will be by Dr. Kanak Saha from the Inter-University Center for Astronomy and Astrophysics, Pune. And the second talk would be by Professor K.K. Nandi. So I'll move to the first one by Professor Kanak Saha, who would be speaking about the early galaxy formation, the information that we have obtained through the AstroSat UV deep field observations like that. We all know that it has been a very, very vibrant area of research work. When the universe had the age of 380,000 years, then we had this decoupling period, and after that the reionization, and following that we had this galactic formation era. So we have got a lot of information from those parts of the universe which had been very, very far off, and Professor Kanak Saha had been a part of this international project. So I would request Professor Kanak Saha now to kindly start his talk on this very, very crucial topic, and we all be benefited by this new piece of learning. Over to Professor Kanak Saha now.
Thank you very much, Professor Verma. Thank you very much for the kind introduction. Also, I like to thank Professor Paul for inviting me to this webinar seminar. So I'd like to now trying to share. So can you see my screen here?
Yes, visible.
Yeah, the screen is visible.
Screen is visible. Yeah, I think I cannot see anybody else now.
Yeah.
So it's probably the Google. So thank you once again. So I'm going to talk today about the probing the early galaxy formation using AstroSat UV field, and there will be a lot of technical aspects here. So I'll try to go at a very basic level, primarily aimed for students. So there's a brief outline. I'm going to talk about like some key properties of the galaxies in short, and then there's an interesting problem that we are addressing in this context is the photon escape, the escape fraction of ionizing photons from galaxies that probably happened in the very early universe and uh, had a like probably had a controlling power on how subsequent galaxies formed. And this is, and then in this context, the that we had from having Astrosat, which is our the own satellite from India. So without going into in the first slide, and I wanted to just show this diagram, so this slide, which will be useful for understanding various some background sounds. I don't know. So in astrophysics, we receive like in the light from stars, and this is a solar spectrum on this, and which can be well fit by a black body, of course, like apart from the absorption lines. And the black body is uniquely specified by one parameter called the temperature. So on the right side, you see a several black body curve, which is at a different temperature. The black one is at 3,500 Kelvin to as you go to higher temperature. And as you know from very basic physics textbook stuff, that as you go to the higher and higher temperature, the peak of the black body shifts towards the bluer side or the shorter wavelength side. And once you go to a very high temperature, for example, if you put temperature on, let's say, just an 80,000 Kelvin, then the lambda peak should appear at 362 angstrom, and such photons are basically can be called an extreme UV photons or ionizing photons or the Lyman continuum photons. In fact, anything that is whose wavelength is less than 912 angstrom, those are in this category. So this would be a useful the terminology, and these are the what I will going to subsequently talk about. This we are the escape of such photons from galaxies and how these were relevant for the galaxy formation. Now in astronomy, we apart from a Milky Way, as you go outside the Milky Way, when you receive light from mostly from galaxies, and galaxies emit in different wavelength. In fact, as you show that the black body itself is you have an entire electromagnetic spectrum embedded in that. So when you observe galaxies, we observe in different the wavelength window. So there could be, like, for example, from ground-based telescopes, we have the access to the visible window of the electromagnetic spectrum, and then we have a part of the infrared, and you can go to, of course, like very higher wavelength in terms of like millimeter, sub-millimeter, which are in the sub-millimeter telescopes or ALMA, and of course India has like a long tradition also in the radio astronomy, which is in the centimeter range, and through which we can probe also galaxies. If you go to the shorter wavelength side, then you have ultraviolet, and as you know, the UV is blocked by the upper atmosphere below 3000, around 300 angstrom. So if you want to study galaxies even at shorter wavelength, you need to go to space. So this is bit a costly affair in the context of, like, compared to the ground-based telescopes. And galaxies, of course, like appear very differently in terms of their morphology. For example, you can see from the infrared on the right side of the same galaxy, and also if you go from the right side to the left, you see the infrared and the optical, and in UV, or in fact in far UV, you can see that the galaxy is almost not visible, which means only a part of the galaxy is probably emitting in far ultraviolet, and this is relevant for or in fact, like, that those are the pass bands or the filters, or if you like that far ultraviolet window would be probing stars which are short-lived and young. So in other words, by looking at galaxies in this wavelength range we are most of the time would be probing the young star forming regions in galaxies. So this is like, I wanted to go see a picture of the Milky Way, because it remains incomplete if we don't talk about the Milky Way. So Milky Way galaxies are basically it's a huge galaxy, more than an L-star mass, and on the left I show a picture of the Milky Way galaxy, which is a sun-centric, made by William Herschel more than 200 years ago. And this is the another artistic impression of the Milky Way galaxy, where the sun goes around the center of the Milky Way with a speed of over 220 kilometers per second. And this is like this artistic impression contains like a lot of valuable information about the Milky Way galaxy. And for those who are new to this, the typical Milky Way type galaxy would contain about 10 to the 10 stars or more. So which means like about 10 billion to 100 billion stars, like depending on how massive the galaxies are. So so by looking at galaxies, like other than the Milky Way in the local universe, we get to know a lot of fundamental properties of the galaxies. But I don't think I will go on to like many this thing. But what is important from is that all those billions of stars in the galaxies, they go in a particular orbit, okay, around the galaxy, and the mean free path of a star are generally much larger than the galaxy size itself. So stars don't collide, so they are more or less like collisionless object. Now that's like theoretical sort of picture. This is how the galaxies are. I mean, this is a collection of like stars, which is like comprises more than about 90% of the mass, the visible mass, and then 10% probably in the gas, like in a typical Milky Way like galaxy. As I said, that the stars don't collide, and so that's the very basic thing that we know in some sense from various understanding from the n-body the numerical simulation, and also like certain observational characteristic that we know. Now, if you look at a galaxy in the sky, like a typical image, this is what we observe through let's say ground-based telescope of a galaxy. That what we can measure from the galaxy image is that distribution of the light in the galaxy, which is like represented as a function of high intensity of the light as a function of like radius. You can like make some distribution. Now from the light we want to know like to know the surface density, which is the surface mass density. You need to know the mass to light ratio. So the mass to light ratio is an unknown quantity. And from the surface density, if you want to know the volume density, you need to deproject the image. And deprojection is also not unique unless the galaxy is like spherical. Okay. And as you know, for obvious thing that we want to know the volume density of the stars, which is we think the light that we see is coming from the stars. So because it's an optical window, so the density is related to the potential. So if you want to know the potential of the galaxy, so you need to know the volume density of the star. So this becomes like sort of roundabout and complex in this sense that you already just from the light, if you want to know the volume density, you have two unknown parameters that we don't know. I mean, there are many other things, but simplest. So the understanding the physics of galaxies is really difficult in if you really want to base your thing from the like theory to the observations hand to hand. Okay. So not, so this is the picture in the Milky Way, sorry, not Milky Way, but the local universe. Okay. So this is one aspect of the problem, because there are many other aspects of the problem that we don't know about the galaxies. Okay, for example, how the stars are forming in the galaxy, with what rate the stars are forming, what is the efficiency with the stars forming galaxy. So these are all a lot of questions related to the forming the stars itself. Okay, and it's not forming at a given instant of time, but it probably does so over a long period of time. Again, that depends on what kind of galaxies that you are dealing with. Okay, for some galaxies, most of the stars form probably very early in the universe. For some, the stars are still forming. For example, Milky Way is forming on an average 1 solar mass per year. Okay, if you take about, for example, 1 billion year, there would be it accumulate to about 1 billion solar mass in some sense. But that is not very meaningful. But the rate, at the current rate, is like sort of 1 solar mass per year. So it's not much compared to early universe in the very early time. The galaxies were probably forming a few tens of solar mass or 100 solar mass per year. Now, I like to move on from the local to the slowly to the high redshift universe, and you can see now I put in the picture of the Milky Way, which is still the artistic impression, but this is good enough for giving a realistic sense. And as you move to higher redshift, which is marked by Z here equals to 0.5, which is 0.5, and then 0.9, and then redshift 1.6, 2.3. If you can move on up to redshift 11, is where the appearance of the galaxy is really not, which is exciting, but due to many other things, partly because of our instruments capability to resolve galaxies at that far away, redshift 10, 11, in that. But wherever we could resolve, and then these are where the contribution from the Hubble Space Telescope made a tremendous impact on our understanding and a lot of revealing from the HST, is that if you go to the middle redshift range, which is around 1.1 to around 2, then the galaxies are clumpy. Okay, which means you see that there are they are not big matured glass, big matured collection of stars, either in the form of a spiral or form of a spheroid, but rather they are from a tiny clumps, which is like a dominant characteristic of galaxies in the redshift 1 and 2. Redshift 1 and 2 are also very important in the history of the universe, is that's when the galaxies were forming most of their stars, because the cosmic star formation history had its peak around that redshift range. So higher the redshift range, we are going earlier and earlier phases of the universe, but not very much. Okay. Now, since we talk about the redshift, so we measure the redshift using the spectral lines. So you could for example, look at for example, this is hydrogen alpha is in one of the optical line. They are 6563 angstrom. You could take strong emission lines from galaxies. It could be hydrogen alpha, it could be Lyman alpha. It depending on the galaxies, it could be oxygen 3, 5007 angstrom. It depends on your galaxy. But if you have an emission line, which you know what the emission line is, and if it is emitted from a galaxy at redshift, let's say Z, then the observed the line will be appearing at a wavelength which is 1 plus Z multiplied by the rest frame, which is the emitting redshift. So we compare the lines in the galaxy and in the lag frame, and we can measure the shift and that's how you can know the recession velocity and also sort of measure the redshift of the galaxy. And this is considered to be like one of the most accurate measurement. And I mean, there's this saying like if we don't have spectroscopic redshift, then we don't know where the galaxy is, and other sources are not very trustable, because that's the most trustable. So there are many other methods. I'm not going to get into there, but I think that's the one. If you know that to measure the redshift of a galaxy, we use spectral line, and various strong emission lines are good for this. Now I show a very comparison, probably not to the mark, but look at, like, think about it. There's a tadpole and there's a frog, and if we didn't, and for example, you show there's a galaxy at redshift 10 and it's redshift 0. Okay. Now we know that the tadpole is evolved to become frog toad, because we have the full life cycle of the frog. Okay. From biological sciences, so we know that it is the tadpole which will evolve toward the galaxy, but evolve towards the toad. But we do not know whether this galaxy would appear like this in the local universe, which is a redshift 0, because we don't have any information about the full life cycle of any galaxy actually. So we cannot study galaxies in this fashion. So we often talk about galaxies, because one galaxy is observed at a time in the sky, and often we talk about the redshift slices. So try to understand some in a statistical sense. So this is a very, very challenging task, that how this high redshift, the early galaxies evolved towards the local one, because it must have been this way. But in between, what are the physical processes that were active and that were responsible for it remains to be discovered and remains to be understood. I mean, there are many physical processes has been put forward to understand this, but you have a coherent picture. For example, if you look at a redshift 0 galaxy, can we say that how many mergers did it go through, or what are the dominant physical processes that shape this galaxy? It's really a challenging task. Just to give you a glimpse of the early galaxies, like the redshift 1, there's a so mosaic of many galaxies here, and you can see that a lot of galaxies, these are all basically the examples of tadpole galaxies with a bright head, and there's a comet-like tail, and these are the tadpole galaxies. And I thought, since I gave an example of a tadpole, I thought I'll show you there are actually galaxies where look like tadpole. So so this is the picture which we are talking about the galaxies. So the main problem is that how with the galaxies, when the galaxies form, whether we know the redshift 10, 11, and in this era, from there they come to the redshift 0. It's a very, very challenging task. Now, on top of that, we don't know also how the first galaxies formed. This is a schematic diagram of our universe at a glance, in some sense. And as you know, those who are in cosmology, they know this picture or the diagram very well, that the universe went through completed the recombination era around 4,000 years, when it was just 4,000 years old, or at a redshift of 1100. And at that time, the universe was filled with mostly the hydrogen gas, so the neutral lifetime. Now, within and about 0.1 billion year from when it was around 0.1 billion year old, that the first stars in the galaxy start forming, and those stars probably form from those almost in a metal-free gas, which is the neutral hydrogen gas, and this probably were the very massive stars, could be like hundreds of solar mass, but there's a lot of debate in this because, as you know, we are probably constantly changing our understanding, changing in this context. So those are sort of those like supposedly like the most massive stars, like hundreds of solar mass, I call the top 3 stars in the context of in astrophysics. And those the stars, since they are very massive, they would be like short-lived and also like very hot. So they would emit a lot of the light in the extreme UV regime. So so those galaxies and the stars, the galaxies that are made from those stars would be like site of the source of extreme UV photons that I talked about in the first slide, and those photons would go on to sort of ionize the hydrogen atom because they have the enough energy, like greater than 13.6 electron volts. So they would they break the hydrogen atom into proton and electron, and that's how an era called the reionization era started, from the neutral phase through the first galaxy formation, and then the reionization phase started. And by around redshift 6, the reionization probably complete, but again, current picture or understanding says that it's probably redshift 5.5-ish when the reionization completed, and now we living in an era which is like reionization era, which means the most of the matter between the galaxies are reionized. Now there is a lots and lots of like question that are coming up in regarding this reionization phase, when and how and what caused, what were the the topology of the universe at that time. And there is lots of questions for us at this moment. What my interest and what I'm looking at, to understand those first galaxies, or in terms of the sources of those first sources that were sources of the extreme UV photons or ionizing photons. So my interest is that what kind of galaxies were they? Okay, how do you probe them? Because this is really a difficult task in that. And then there is a as you know, because these first galaxies did not form everywhere. They probably formed in localized patches where the dark matter collapsed locally from probably mini halos. So they were not everywhere. So this must have been patchy. So and then when the first galaxies formed, the photons would escape from them and then ionize the surrounding hydrogen gas. Then in that case, it would be useful for us to know that how the subsequent galaxies also sort of formed, and what fraction of those photons, ionizing photons, that escaped and reionized the surrounding hydrogen gas, right? So this escape fraction, the UV escape fraction, it remains one of the unknown parameter at present, and we do not know also. There is no direct observation of such galaxies at present in this redshift range, where we have actually observed extreme UV photons. Now, you can see there is a huge also the search of literature or the studies research recently on this escape of ionizing photons. And here I am going to talk very briefly about the problem of the escape of ionizing photons. And what happens is that imagine in a galaxy, in a various nebulae where the stars form, and when the light from the stars would try to ionize the hydrogen gas, so there will be a layer of the ionized hydrogen around the starburst region, followed by a neutral hydrogen gas in that. And if you calculate the mean free path of the ionizing photons, which is basically 1 over the cross section times the neutral hydrogen gas density, it seems that that number, the mean free path, is like sort of less than a parsec in length. Then whereas the size of this neutral, the boundary of the neutral hydrogen gas where it goes is something like around few tens to 100 parsec, depending on the central starburst, like the strength of that. So the ionizing photons would easily be absorbed by the hydrogen gas and or probably the used in the dust. So they don't escape easily unless like there are channels of low density gas and dust through which these photons would escape. Okay, so that's the kind of like problem that happens in the interstellar medium of the galaxy itself, like in the interstellar medium. Now, this is the schematic picture that I have drawn here, where I show in the center there is the galaxy with the ISM I marked here. So as you can see, like if some photons try to escape this the interstellar medium, they would be like have to go through the circumgalactic medium, which are in probably like abundant in high redshift or the early galaxies. So those photons, ionizing photons, would be absorbed in the hydrogen gas of the circumgalactic medium. And even if some try to manage to escape the ISM and the CGM of a galaxy, they would have to travel from all the way from the galaxy, from the early universe or wherever the galaxy of your interest is, to you through the intergalactic medium, which is also filled with like hydrogen gas, and they will be absorbing the photons. So at the end, you see when you receive photons, there are only minuscule amount or probably none. That I'll show you that it is only in the last 4 years that this has been like growing tremendously in terms of like detection of these photons. So it's kind of very difficult, and if you concentrate on the red line here on this curve, it shows the transmission probability of the intergalactic medium versus the wavelength. But if you mark, this is the observed wavelength, but if you look at the each are marked with a vertical line here, which is the redshift 6. So by around redshift 6, which is the reionization era, the transmission is nearly 0, which means we do not receive such photons from those galaxies, and hence we do not also know the nature of those galaxies in some sense. So this is a really challenging task in some sense, detection of these photons, and we know that if we don't know those, then we don't know what happened in the reionization era and how those galaxies formed, what were the characteristics, and it's really, in other words, we need to know this something called a parameter called the F escape, which is the escape fraction parameter. That's the very key. So you can see like of course since if we can't do it at redshift 6, we try to like come down to comparatively low redshift, say redshift 2, whatever, where the transmission is generally high, or even in the local universe, there is at least the IGM will not be of that much of an issue to understand or to measure this escape fraction from galaxies. So here where I start and sort of like briefly we will go through the contribution from the AstroSat on this aspect. AstroSat, of course, for many of you know that it's India's first space observatory. It's launched almost like around 6 years ago. And we looked, using AstroSat, we looked into a blank patch of the sky in the southern hemisphere, which is centered around the famous deep field called Chandra Deep Field South or Hubble Deep Field. And we observed this patch of the sky with the UVIT AstroSat. And the UVIT is a telescope which have two telescope which are co-aligned and not a big one, with an aperture of only 37.5 centimeter, and this instrument payload manager is Professor Tendon and from IUCA, and this was built in collaboration with multi institutes, Indian Institute of Astrophysics in Bangalore, IUCA, the TIFR, Canadian Space Agency, and ISRO. So we, and unfortunately, of course, one of the telescope is not working now. It's only the one is working at the moment. So we are fortunate since we were beginning, we observed this field. We had both the telescope were working, which is called the far UV, the FUV telescope, and the NUV telescope. And in FUV and NUV telescope have 5 filters through which you could observe. We use one of the filter whose mean wavelength is around 1500 angstrom in the far ultraviolet, which is called the F154W. And in the near ultraviolet, we observed with the 2400 angstrom, which is the 2418 angstrom is the mean wavelength, okay, which is N242W. Like this terminologies, you probably wouldn't remember by the time probably talk is finished, but that's okay. So, but essential thing is that one is a shorter wavelength, which is centered around 1500 angstrom, and one is 242 W, which is around 2400 angstrom. These are the observed wavelength. So the UVIT, the way it was observing, like it observes simultaneously both in FUV and NUV, and between 2 successive frames, there are like around 33.8 milliseconds gap. So it's like very fast. So in a typical good dump orbit that we organize the observation, and the data is around 1500 seconds. In 1500 seconds, we can, this is a typical dump orbit, we have around 45,000 to 50,000 frames, and depending on the time of the observations and various other parameters, there could be like several frames which could be lost due to the cosmic ray showers. These are some of the frames in which you can see like the incident photons, but these are the cosmic ray affected frames. So these are generally removed from the pipeline towards making the final image. This is one of the one orbit dump orbit image. So another dump orbit image. So we have like around 40 such dump orbit image. And
এইভাবেই ছিল প্রথম থেকে, আজ থেকে নাকি জন্মের আগে থেকে দেখছি ওইটা, ওর পাঁচের ছিল, এখন
hello.
May I request some participants to kindly switch off their microphones so that the speaker can speak well.
Thank you. So we look at this you can consider one of the frame. This is a field of view. The circle that you can see is in the shape of a circle. It has a diameter about 28 arcminute, and in this one orbit image you do not see much. Actually, it looks like very noisy, and but you can still see some like dark spots. So which are some objects in the sky, and then these objects will appear at different location in this field of view. And what we do is like we take one of them as a reference, and we align all other frames like of the dump orbit image by applying shift and rotation, and then like join together and to form a final image, which is with observations taken over a longer period of time. And this is how it looks like, let's say in one orbit in a zoomed in view in far ultraviolet and near ultraviolet. So this is mostly you can see like this one orbit image quality, and this is how it looks like in when I combine 40 such orbit. This is the AstroSat UV field in near ultraviolet window. And you can see here there are several. This field is a very, very famous, and lots and lots of telescopes have observed before us. And a famous one is the Hubble Deep Field, which is in the blue squares in the central region. And this also contains the Hubble ultra deep field, and also the nowadays the Muse extreme deep field in the same region. And this is how it looks like if you look at the same image in a color with many other telescope image. So I'll just go into this image. So this is a patch of the image which is made in 4 wavelength, 2 from the HST and optical, and 2 from Astrosat. As cyan and blue are from Astrosat. What is important for us here in this Astrosat UV deep field, when you look at that, is the faint objects that we are mostly interested in, because the one of the aspects of the deep field is that we were interested in looking at the farthest and the faintest and the farthest objects actually. So when you measure the 3 sigma detection limit within 1 arcsecond aperture, we get around 27.9, and if the same far ultraviolet window, like sort of a similar filter in HST, this was around 27.4 magnitude, and so we could go about half a magnitude fainter objects than what HST could do using in the same filter. So this was a big advantage for us. In fact, this is what the main thing. Now there are also many reasons why you should study deep field, and there are many things. One of them is obviously my favorite is the luminosity function. This is the galaxy luminosity function in what is plotted here. You can see that the luminosity function is the number density of galaxy per unit, the magnitude range, and on the x-axis this is the absolute magnitude. And you can see the observation shows almost flat, but it is not clear what the slope is. The slope is alpha, and we are interested in constraining this faint and slope in the UV. There is another one which I was talking about, that the Astrosat UV deep field is ideal for probing those ionizing photons from redshift 1 to 2. For reasons is that at redshift 1, the entire Astrosat filter, the filter has character the bluer side wavelength and then the redder side wavelength. The redder side wavelength will be all within the Lyman limit. Okay, I don't know if I'll have a picture later. I'll explain. So so this is a very promising thing for to do with Astrosat. So before Astrosat, we had 2016, when our observation was we got it was probably going on, and then we had the first set of detection of Lyman continuum photons from low redshift universe, which is around redshift 0.4. Okay, so these are the green peas and the blueberry type galaxies. They're a compact starburst galaxy. Okay, then in 2018, when we are still working on the pipeline, there were a group from the CAKE who published a number of Lyman continuum emitting galaxies from around redshift 3. So between redshift 4 and redshift 2.5-ish, this is called the redshift desert, not redshift desert, but the LYC, it is the Lyman continuum galaxies, the desert for the Lyman continuum galaxy, because there are no observation before Astrosat. So and before this 2016 and 18, there are only 3 or 4 such detection. So you can see that in the last 4 or 5 years, there's a huge increase, and now it's going even more. So this is what I was trying to explain here, is that this is the FEV filter, that you can see the filter response curve here. And with redshift, we have one detection, which I'm going to talk very briefly now about at redshift of 1.42, and at redshift 1.4 to the Lyman limit, which is Lyman limit is nothing but 912 angstrom multiplied by 1 plus z. So that would be around 2200 150 angstrom. So which is but the FUV filter, you can see that's all within the Lyman limit, which means the photons that will incident on this filter, they will be like Lyman continuum photons or extreme UV photons or ionizing photons from this galaxy. And this work published in 2020 in Nature Astronomy, and this is a collaboration work with many people from here and as well as outside India. So we did a thorough selection, because you can see, like, I showed you an image. Now of this, there is a one galaxy that we are looked at. Now, how did we do that? We did look at around 1500 galaxies with spectroscopic redshift, which means we know the redshift very well. And then we only downsize the sample by various criteria. And we looked at thoroughly about 38 objects in the Hubble Extreme Deep Field. And of these, about 2 came clean, one that a signal to noise of greater than 3, and one that we chose to work for which something called the equivalent width of the hydrogen alpha line and this O3, which is a doubly ionized oxygen line. The equivalent width was very, very high. When the equivalent width is very, very high, it means that there is a lot of young population in the galaxy than the older population. So this is the galaxy, which is in the black and white, the grayscale image of where the galaxy is within the red circle. It's almost like a noise. But if you zoom in, you see there is a detection barely cross 3.3, signal to noise of 3, and this is the objects we are going to talk. And of course, at the same location in the near ultraviolet filter, we have a very good detection from the near ultraviolet window, but the near ultraviolet window is not useful for studying the ionizing photons of this galaxy, because this has a photon which will also be more than 912 angstrom. So it's not good. So it's a mixer there. Now this galaxy is observed in many other pass bands. So in many different, with a particularly HST, within Spitzer, and also in VLT, but not in GALEX, for example. And also we have a MUSE, which is the spectroscopic the survey. This galaxy was also not MUSE data. This is how the galaxy looks like, which is four major clump in the galaxy. The galaxy within the red dashed circle is that is there. This is the HST image. It looks like much sane and much better here. All the 4 clumps were there in the galaxy, but then there were several questions came to us that whether all the 4 clumps are at the same redshift. Do they belong to the galaxy? Could one of them be at foreground, so that you are actually seeing along the line of sight? So there are many such questions, but we had to, we were lucky to have the GRISM spectra from this galaxy, and as we we analyze the GRISM spectra, when we do basically which is called the emission line mapping, and this is where the emission line mapping is being done for this galaxy, and we identify from 2 clump, which is C1, C2, C3, and C4. These are the spectral lines. So like at A, B, and C is the inset figures here, and you can see that on the wavelength around 1.6 micron, where there was the observed wavelength of the hydrogen alpha, and this is that line when we identified with the hydrogen alpha, we found that all the clumps are at the same redshift, and we sort of confirm that this is one galaxy is basically a clumpy galaxy. And we did, since we had a lot of multi-band observation from far ultraviolet to all the way up to infrared. We could do detailed ACD modeling, which is called the spectral energy distribution modeling, and which shows that the galaxy is actually low mass. This is a very good for measuring the stellar mass of a galaxy. Okay, which is very accurate in many sense, although it's a model dependent, but still. And it's showing us the star formation rate around 55 solar mass per year, which is at the forming stars at a rate of 55 mass of sun per year, and is sort of not very metal poor, but it's like metal poor galaxy. What I wanted to say is that like the clumpy galaxy, you have many galaxies between redshift 1 and 2, which I've been saying that they are actually clumpy. So this observation will open up for us to look at the kind of galaxies for which we could expect Lyman continuum photons, so the ionizing photons. In other words, now the reason is that we were stressing on this is that we don't know how the first galaxies were. They were clumpy, they are like compact, like those green peas, blueberries. What kind of galaxies they are? Like what do they look like? You know, lots of question comes to us for that. Now, so this raises the hope of basically looking for Lyman continuum or this leakage from clumpy galaxies, and clumpy galaxies are norm rather in redshift 1 to 2. Okay, so here is what the last slide almost, and here I'm going to measure the fraction of the escape photon, the photons that could escape. So what we do here, we do a very textbook stuff here. We assume like something called case B recombination within the galaxy, and we estimate the number of ionizing photons that could not escape. Okay, so which means they were used in the recombination and process, and we can measure that number of photons by measuring the for example hydrogen beta line, but hydrogen beta line is quite weak, so we use the hydrogen alpha line through like some small manipulation here, and that's how we estimate number of ionizing photons that were used in the recombination process that could not escape. And from the AstroSat filter, we calculate the luminosity of the photons or the light that we receive from the galaxy. And that's how we estimate the total number of photons that ionizing photon that escape the galaxy. And then escape fraction is nothing but the photons that escaped and total number of ionizing photons that is produced. So this came very clean as like 0.2, which is like around 20%. So we did like quite a bit of other statistics, or there are other methods being also applied, but what is very basic, what is clean is that this is the galaxy which is sort of around 20% of the Lyman continuum photons probably escaping this galaxy. So this is kind of a the right kind of a galaxy that you would want to have at the early era, especially in the era of the deionization era. So but it remains to be like explored, so we don't know yet. So with the X3, this after AstroSat, we have one data point now, but you can see the data points are color coded. Most of the discoveries or the detections so far happened at the rest frame wavelength of 900-ish angstrom. Ours is the first one, which is having 600 angstrom photons. So this is the first galaxy caught with a rest frame wavelength. Rest frame wavelength is around 600 angstrom. So this is a very good thing, and then soon this part is basically space will be populated. I think we have another paper which is in the pipeline right now. So but I think With the AstroSat, this is basically is possible now. Now with I'm just close to the end now. I'm going to finish this with this slide that we have now lots of observation of the similar around the area, and you can see that we are now coadding all those observations together and making one of the deep field in UV. So this will be very useful for many surveys upcoming, and there is no other FEV telescope anymore. So these are some of the team members who are still active, and we are all working. And then with this, I'd like to end my presentation. And if there are questions, I'll be happy to.
So at the end of this talk, I'll invite questions. I can take just a few questions from the audience if you want to.
On now. Sit down, please.
Can I ask you, Kanak, one thing?
Yes, please.
You talked about this Z equal to 1.42, right?
Yes.
And I was wondering, what information do we have about the distance to this object? I'm sure that will throw light on the curvature, or that will depend on the curvature of space-time, space between the source and the detector, right? But do we have some clue about this curvature from there? Can we have it?
Yeah, I was wondering whether the curvature will become important even bit of a higher redshift, like redshift beyond 4 or something. But I don't know. I mean, we are use that just a luminosity.
But why he is not moving? It doesn't show the motion.
Sorry?
I think there are some microphones are on. So I will request throughout the lectures, in fact, to keep the microphones off, on the part of the participants. It would be nice. And also see, what about this gamma ray observations or something? If you go so beyond this Z equal to 1.42, if you go to the higher redshifts, then obviously you'll have, say, hotter and hotter. And then the gamma rays or X-rays, can prove to be more informative. Is it so?
Yes, I think people already started looking at probing.
Okay.
So there is the X-ray binaries, and in that, so there is of course, like you have active galactic nuclei, for example. They are
That's
also
right.
like but I think there is a debate which is on now.
Okay.
Is that quite some time ago people used to think that no, we don't need actually this kind of galaxies, because we have AGN, active galactic nuclei, so they could be enough for doing the reionization. But it seems like when you talk about the number density, I did not go into those direction, but it seems like the you don't have enough of such bright objects. But now it has gone into another stage now, talking about faint AGNs in the galaxies. And what about the faint AGN? Their number could be large. So you see, the main point is that one of the point I'm talking about is that the galaxies that are thought to be ideal is not actually bright galaxy. These are like the faint low mass galaxy whose numbers are large. So they were thought to be the prime candidate for the reionization.
That's true. Yes.
So and then whether they had AGNs or not, like small AGNs, or those are kind of I think it's a hot debate now.
Yeah. Okay. So do we have other questions?
Some questions.
I have one question.
Yeah.
Professor Shah,
Yes.
your observation of the faint galaxy in ultraviolet regime of the astrosat, isn't it?
Yes.
Yeah. Now, this kind of galaxies are many or few. That means you have discussed only one, or there are others also. If you probe your instrument in other direction.
Oh no, because you see, sorry, I don't need to like go into the slides, but I think in the same field
Yes.
there are already many other sources which are
Yes.
like this. We have just worked on one of the objects, which I tried to motivate, why? Because this was a very, this is like a starburst galaxy.
Okay.
So we have bit more than 10 candidates now, which will come out soon. For which we know that there is the Lyman continuum photons, escaping Lyman continuum photons. So we had actually big patch of the sky. So all we need is lots and lots of spectroscopic redshift measurement. So
Okay.
we are limited by that because
Oh.
we don't have the spectroscopic redshift estimate for all the, it's a big challenging task in some sense. Or like someone has to invest a lot of time in telescope time doing that. So once you have the spectroscopic redshift, we have already a pretty good UV observation and which we can just go on. So we keep waiting for spectroscopic redshift to be available.
Yes.
You see, that is the main thing. And this kind of galaxies are actually the ideal. These are the low mass galaxy. You see the mass is 1.4 into 10 to the 9 solar mass. So they are not massive. They are not massive like big Milky Way galaxy. And these galaxies are supposed to be, this is what I try to explain through the luminosity function, that there will be many such low mass galaxies.
And what is the approximate distance from our galaxy? Approximately.
I don't know. This luminosity distance is like 9.3 billion light years. So
9.6 billion light year.
yes.
Very huge distance.
But you talk about the redshift, so 1.4.
Yes. Redshift tells you where the galaxy is.
At least numbers are like same.
Yeah, that's really wonderful.
Okay. So is there are some questions in the chat? Should we?
Yes.
Go on to I do not know.
Well, I don't see any questions on the chat. Yeah. So if there are no questions, then
There is question from Devumallo Mukhopadhyay and Anmol Giri. Have you seen Dr. Shah?
Okay. Yes.
Yeah.
Clicking on
There are
it.
two questions, right?
Why majority of the galaxies are spiral in nature?
Yes.
I mean, I could go on answering this. It's but I think this is a generally sort of out. But but this is really not true in a sense that the majority of galaxies are not spiral, because if you look at so that is how one is to look at where you want to actually look at the galaxy density in some sense. So if you look at a cluster of galaxies, let's say, which is very rich cluster in some sense, which contains typically 1,000 galaxies. So in a typical cluster of galaxy, most of the galaxies are actually not spiral. Okay, so it depends on how you look. Depends. You have to set your window where. Then if you go on a group, which is of course only a few galaxies. So depend on how where you look. Now so Weaver has asked this question, so I hope you can hear. But this is the important part, that where are you actually looking? So if you look at a big cluster, the rich cluster of galaxies, then it is the majority of galaxies are actually not spiral. They are early type, like elliptical, lenticular, different morphology.
That's right.
Not have spiral structure.
That's right. And we have another question from Anmol Giri, do the photons in the talk contribute to the Lyman alpha forest observation? And if yes, then what are the implications on the cosmological models?
First of all, I don't have any answer for this, like how it will constrain this.
Yeah.
But we don't have a Lyman alpha line observation in this galaxy, so we don't know
Okay.
how to measure the forest here. But it's interesting. So if we have a HST observation, probably we should be able to answer this.
Yeah.
In the spectroscopy.
So good that in case we don't have other questions, we can move to the next speaker. Thank you very much,
Thank you.
Professor Saha, for this brilliant talk. And this restored our faith in this AstroSat. So let's have a clapping for Professor Kanak Saha. No, all of us, wherever we are, we can at least give a big hand to Professor Saha's talk. We are really thankful for making it such a nice presentation. And next, we will move to our next speaker, Professor K.K. Nandi, Professor Kamalkant Nandi, who did his PhD from, let me introduce the second speaker. He did his PhD from IIT Chennai, Madras, and he was also professor at the mathematics department of the North Bengal University. He had been an eminent mathematician. At present, he is a professor of the Bashkir State Pedagogical University and director also of the Zeldovik Institute, Zeldovik International Center for Astrophysics in Russia. Professor Nandi would be speaking on a very important topic, the gravitational time advancement, which has been rather kind of a test for our general theory of relativity, because it speaks a lot. And it's also called the Shapiro effect, the time delay and all that. It's very important. And this is also related to my question earlier to Professor Kanak Saha, where I had asked him as to whether this curvature of space-time plays an important role in the time delay. So yes, it does. And so far, we have got a very good confirmation of the general theory of relativity by several observations. And this is certainly going to be a very, very important one. So I'll request Professor Nandi to start his talk on the gravitational time advancement.
Good evening. Good evening, my friends and colleagues and students in India, ladies and gentlemen in India, and some are here. As you know that I am talking from Russia, and we are a bit worried here because Russia is at war. But still, since I agreed with Bikash, so I'm giving a talk, but with some kind of anxiety in the mind. So I'm talking about something not simple. Actually, it is very simple. Therefore, I decided to discuss this topic of gravitational time advancement, which should be, everybody can understand it. It is very simple, but it is a new effect, which we think new. Anyway, so here we begin without losing time. You must have heard of this Shapiro effect, which is, in general relativity, it is one of the premier tests of general relativity, which is Shapiro time delay effect. What has been done in the experiment is that you send a light signal from Earth to Mercury in the superior conjunction, which means when Earth, Sun, and Mercury are in one straight line. So you send the signal to Mercury, get it reflected from Mercury back to Earth. So you calculate the time taken. Now you know the Euclidean distances between Earth and Sun and Mercury. These are known. You will see that there is an extra time needed you have the Euclidean distance, Euclidean time, you need some extra time. And this extra time means it is delayed. It is slowed down. Gravitation slows down light because it takes more time than it should have taken in the absence of the mass, namely the sun. This is a Shapiro delay effect. Gravitation slows down light. This is the knowledge that we have learned from that experiment. So we want to say that this is just half of the story. The other half of the story is the following. Can I go to the pictures? Other half of the story here. Now think about this situation. Earth and moon. Okay, gravity is strong here. Gravity is comparatively less here. What will happen if you send a light signal from moon to Earth and back to moon? You will find Shapiro time delay. You can calculate it. You will find it delay. Time is delayed. Again, I repeat, time delay, I mean there is the Euclidean distance, but since light is slowed down either way, to and fro, it takes more time. This extra time is what is called delay, Shapiro delay. Go to the next one. Now the question is, what happens if you send the light from Earth to moon and back? Actually, this is what you call lunar laser ranging, LLR experiment. That's how you measure the distance to the moon, right? You send a signal, get it back, and measure the time. That's all. Now, our argument is that if you do this experiment, the clock is now here, not there, but here, then the clock C1 will not measure time delay. It will be negative time delay. This is what we have decided to call time advancement. Again, it is not just a reciprocal of the Shapiro delay. That means, I mean to say, if the Shapiro delay is 5 seconds, it doesn't mean that the Earth clock will measure -5 seconds. No, it is asymmetric. That's why this is a non-trivial effect. So this is what we want to say. In other words, we can say that the distance to the moon that we know today is actually a little less because of this effect, because of this time advancement effect. So this is the main thing, okay? The rest is just calculation and etc. So the main thing is this, that the distance to the moon is slightly less than we know. It is not because of some technical error or something, no. It is a physical effect. Because of this, the distance to the moon will be less than we know. No matter how precisely you measure it, it will be less. Because of this time advancement, because the time measured by the clock C1 will be negative delay. Okay, so this is the whole idea. In fact, I can stop my talk even here without going into the details. That's all that I want to talk about. Okay, can they see this motion? Okay, all right, now on to the next one. First. Okay. So Shapiro delay, which I already told you that you send the signal to the Mercury, grazing the sun and get it back, and the Earth clock measures the delay, which is 240 microseconds over the round trip time along the corresponding Euclidean distance, that is without the sun. And this is an excellent agreement with the measurements. This has been tried several times, and it is true. It is always true. Therefore, this is an effect. What we say that now this is positive. Why it is positive? As we where do you here? It is here. Your clock is here. Remember, this is Earth. This is Sun. Now, just assume this is Earth, Sun, and then Mercury. Oh, in short, your clock is a weaker gravity field. You send the signal to the strong gravity and get it back. So your clock is the weaker gravity field. You measure actually time delay, Schwarzschild time delay. That's what Schwarzschild did, because the clock was on Earth, which is whose gravity is weaker than that of sun. Therefore, you measure the delay. This will always be the case. But if you make this choice, that is, your clock is now here, that is, just do the Shapiro experiment, not with the Earth clock, but with the clock in sitting at the sun, which is not possible. But if you did that, you would get negative time delay, not positive. That's the argument. Okay, so if the clock is in a stronger gravity field, you get negative time delay. If it is in a weaker gravity field, like in the Shapiro experiment, you get delay. Okay, so therefore, what happened was, after this experiment, nobody ever thought that what if we did the experiment in a reverse way? The result will be negative. That means the distance to moon will be less than we know. Okay, come to the next one. First. Okay. So this is, I have not prepared my slides in a standard way as other speakers do, but in a sort of, okay. Now, this is time advancement. As I already explained, that your clock is at the strong gravity, and you are sending from strong to weak and back to strong. Your clock is at the strong gravity, and you will measure negative Schwarzschild delay, which we call time advancement. All right, so this is one. Well, we want to, well, by itself, this is a new effect which was published in 2010 in GRG. And some other people all over the world have a little bit of work on this, but we decided to emphasize on this work once again. And here I am with this. Because in 2010, there was a paper in Nature, not our paper, some other people. There is a binary system around the pulsar, okay, around the pulsar. And this they found, because the light is coming from the binary partner via the pulsar to Earth. So it suffered Schwarzschild delay because Earth is a weaker gravity field compared to a pulsar. Therefore, they could calculate the entire system, and they used the Shapiro delay effect. Okay, so therefore this is very much used. And there are other papers too, very much used in ascertaining the astrophysical situation, the configurations, binary configurations, this and that, using the Shapiro delay. Measured on Earth, remember, Earth is at a weak gravity, therefore you will always measure delay. All right, now, so there. Okay, so I can talk about this, but we decided in the meantime to discuss a little bit the effect of this time advancement, which is a new effect, I repeat, on bumblebee gravity. It is a very strange name, but you know, it is not my, I have not given this name, okay? It is called bumblebee because bumblebee is a small thing. Just to think about a flat space, a plane, and put a bee there, just a little bit of disturbance there, okay? So therefore, it is no longer a low-range invariant, okay? Because you spoil the planarity by putting a bee there. It is my understanding. Therefore, it is not low-range invariant. So this bumblebee gravity is not low-range invariant, okay? It violates low-range symmetry. That is the plane, you know, you have this Minkowski plane, and it is invariant under Lorentz transformation, etc. But this is broken if you have a little bit of curvature somewhere, then it is no longer low-range symmetric. All right. Now, it is said that in theories of quantum gravity, it is so far it is very difficult to find the predictions of quantum gravity in the experiments done with the laboratory energy scale, whereas quantum gravity tests require very high Planck energy scale, which is about 10 to the 19 GeV. So people thought that whether we can use bumblebee gravity, which is actually inspired by particle physics. I do not know particle physics, but inspired by this, I know the actions following from it. It is similar to the bumblebee model of gravity. I will show you. I will show you. Oh, it is not here. I'm sorry. I didn't print it here. It is some other. Okay. So let us come straight to the following questions. It violates Lorentz symmetry. Lorentz violation. It is nothing to be worried. Don't be scared because it is possible. Because what is Lorentz symmetry? First of all, we must understand it was a work we did long ago with Dr. Swapan Ghoshal and others. That Lorentz symmetry is actually the invariance of Minkowski spacetime, of course. It is actually a combination of real physical effects of length contraction, time dilation, and arbitrary convention of clock synchronization. It is a convention. How you will synchronize your clocks is up to you. It is a convention and nothing depends on this. Physics doesn't depend on this. Therefore, only this part will be changed. That's all. If you change the convention, the Lorentz symmetry will be broken. But all the real effects will remain as they are. So you see, there is nothing to worry about. It is taken as a sort of a probe of finding the new physical effects in new theories. All right, so that's about it. There are very good papers on this, and they are all there at the end. Okay. Now this is the black hole solution. It is curved like black hole. It is symmetric. It is spinning black hole, as you can see. This L is the Bumblebee parameter. Okay, this is the quantum QG parameter, Lorentz violating parameter. Call it whatever you like. If you put L equal to 0, you get a Kerr metric, which you already know. It's the spinning black hole of general relativity. But now it is not general relativity because L is there, which spoils Lorentz symmetry. We know that general relativity respects Lorentz symmetry, whereas this doesn't. And however, it has a conical symmetry, which I published in another journal. So this L represents a conical symmetry, not planar symmetry. Okay, all right. So this is the spinning black hole of Bumblebee gravity. L is the Bumblebee parameter. What we wanted to test was how this L influences the time advancement that I told you in the beginning. So this is the expression for time advancement. As you can see, as I told you, this is the Euclidean part, and the remaining are the additional part, which is the delay part, Schwarzschild delay. And we calculated it up to third order. There is no problem. Okay, my colleague is here, and he did all these things, third order calculation. So here. Now, listen to it very carefully. This is the time. This is the ordinary. If you calculate, you get it by simply integrating the null geodesics. Even every student knows that. So you get this up to third order. Forget about other orders. Just this term and the first order, and at best you can consider the spinning term. Okay. So this is the Shapiro delay up to third ppn order. Don't bother about third order. One is enough, but okay. Now the point is the following. What is this? This is T is the coordinate delay. Okay, coordinate time. In general relativity, there are coordinate quantities and proper quantities. The time that your clock is measuring right now is proper time, because in gravity, you cannot measure coordinate time, okay, because of the universality of gravitation. Therefore, here, you have to consider the proper time. This is the Schwarzschild delay as this expression, I mean, in short, this expression, full expression. And you multiply it by this, because this is now the proper time that an observer measures at B. RAB, I showed you what is RA and RB. RB is the radius of the Earth, and RA is the radius of the Moon. And time AB is going from signal going from Earth to Moon and back. Okay, so you are on Earth, so your clocks are influenced by the potential of the Earth, which is given by this general relativistic time frequency, or God knows what it is called. That's all. So proper time. So you can expand it a little bit because m by r is very small. So it is this. Now, if you use this TAB, mark it very clearly. If you use delta TAB, which is nothing but this, which you can calculate by integrating the light rays. This is this. it is written in again this TAB, then you will get something interesting. You can find this delta tau CAB, that is this quantity 6 becomes 3 parts like this. 2 means 2 way, don't worry about it. So this is the first term depending on mass, and this is the term mass square. This is the term due to rotation, mass and rotation. Okay, so if you write it, and this equation, just concentrate on this, forget about other terms there, because they're very, very small. We have computed it between the Earth and Moon system. You see, this part is negative. So whole thing is negative. In the case of Shapiro delay, you will see that it will be positive. I'll show you. Now, remember again, your clock is at RB, that is on the center of the on the surface of the sun. Earth, and this is what your clock is. This is what your clock should measure. And this is the coordinate thing which you can never measure, and this is what you can measure. This. Now, if you break it up, you will find that this is the Schwarzschild, this is the Euclidean distance. Sorry, this is the Euclidean distance. This is the effect due to the first order term, and there is a negative side here. That makes all the difference. And of course, you can see the influence of L here, which is bumblebee parameter. Now we go to the forget about mass and rotation square terms. Okay, but you can see the parameter L there, but I don't want to waste time with this. Now look at the other side. That is, your signals are sent from Moon to Earth and back to Moon. Moon is a weaker gravity, so now it will be RA here because your clock is now on the Moon. Okay, and you are in the gravitational field of the Earth. So you will find it. This will be the expansion, and you will find where is this? Didn't you write it? No. Just sorry. Okay, somehow it is not written here, the full expression. Let me see if it is somewhere else. Sorry. Okay, it is just missing here somehow. So if you calculate this, that is your clock is now on the surface of the Moon, then you will find this time, or this into this, and you will find this is positive. This delay is positive. It is Shapiro delay. It is called Shapiro delay. And in our case here again, as you will see, that here the clock is at RB here. Okay, so this gives you, finally this gives you this expression, and this expression is called negative. This is negative delay. Whereas in this case, where the clock is at RA, that is on the Moon, you get a positive delay. The expression is not given here, but you understand, you trust me. So what we have found out is that the Moon observer, the Moon clock will always measure delay. You see, it is positive, delta t. It is always positive. Positive means positive addition to the flat space Euclidean time. Okay, this is always positive because your clock is in the weaker gravitational field. But if you are in the stronger gravitational field, RB, you see, then you will see it is there is delay here, like Schwarzschild positive, delta t is positive, like here, positive. But then it becomes 0 at some distance, and then it is negative. You see, this is negative. This is the negative time delay that we have been talking about. This is positive delay, this is negative, and this is 0. Okay, so there is a distance where there is neither delay nor advancement. It is there, and it is somewhere in between. If this is the radius of the Earth, then the radius of the Moon is something 3 into 10 to the power 10 centimeter. So it is somewhere in between, halfway somewhere. There is a line, there is a point, a surface where you send the light and back, and there will be neither delay nor advancement. So okay, now coming back to the bumblebee effect, the quantum gravity effect, as they say. So this is your primary, the Euclidean term. But as you can see, that it is not exactly Euclidean. As I said, it is Lorentz violating. So there is a term here, small term, 1 plus L. So you will get, this is the extra term, which is called the contribution, Lorentz violating contribution to the Euclidean time. So what will you find is this. And this is the Lorentz violating, LSB means Lorentz symmetry breaking term is this. And how to calculate it? This must be less than 0.8 into 10 to the minus 4 nanosecond. So it will be around this. Now, why do I get this value? It is from the Cassini aircraft experiment, which gave us L equal to less than 6.2 into 10 to the minus 13. And if you put this value here, you get something like this. So this is the Lorentz violating time delay. And you can, it is measurable because now clocks are very finely measured up to picosecond level. This is much less than that. So this is, this could be measurable in time. Now, the main thing is here. If you don't bother about this Lorentz LSB delta tau, you can get, this is the mass effect. This is the rotation effect, which is very, very low, 10 to the minus 10. The rotational effect means first order spin effect is this, and this is delta t, you know. As I showed you that the delta t has 3 components, this plus this plus this. This is the basic component, and this is what you will get if there is no bumblebee. If there is bumblebee, your reading should be like this, okay? So these are the predictions, our predictions. Now, this is the delay. You see, minus the Schwarzschild delay of 1.46 nanosecond. This is very much measurable in the sun, in the moon and Earth experiment. You send this signal from Earth to moon and get it back in the laser ranging experiment. And this corresponds to about 23 centimeters roughly. So this will be the distance less than you know the Earth-Moon distance to be. Okay, so this is a new effect. It is not a technical error, but it's a new effect. But if you have a stronger gravity field, like you sit on the near the horizon of a black hole, you will see the whole of the universe at a go, because this distance will be so small. Because distance is so small, if you multiply by c, so naturally the distance will be less than what you know, than the Euclidean distance. And when you have a very strong gravity, this is for Earth, remember, Earth and Moon. So this is for Earth's gravity. But if you sit near a black hole, this will be so negative that almost the whole of the universe will come to your doorstep. You can see them. Okay, and this is true. I think I read it somewhere, some similar thing. Okay, and this is, if you take a satellite instead of moon, what is the distance of the satellite you have taken? What is the satellite distance? Where? This? Yeah, okay. Radius of the Earth. Yeah. This? Yes. Distance between Earth and satellite. Okay. So you say it's about 36,000 kilometers. If you take that distance to the satellite, Earth to satellite and back, not moon. It is possible to do this experiment, Earth to satellite and back. Then you have this picosecond level advancement, time advancement. That should be negative here. Picosecond level advancement. Okay, this is always observable. So this is the conclusion, that we have a new effect which is called time advancement effect, and it is measurable, and we have calculated between Earth and Moon and between Earth and the satellite. Whichever experiment you do, tables 1 and 2 tell you the values that you expect to observe. So this is the thing. The main thing is the distance that we know are not really what they are, but less or more, depending, you know. But remember, whether it is advancement or time delay, the physical effect is the slowing down of light. This is certainly true in both cases. The question is where your clock is. You could call it a proper time effect, yes, where your clock is. If it is in a strong gravity field, I repeat, if your clock is a strong gravity field, you send a signal and get it back to the strong gravity clock, it will be time advancement. This experiment has not been done, and the Shapiro experiment was the other half of the story, as I said. His clock was on Earth, which is the weak gravity field, and the signal was traveling around the strong gravity field and back to Earth. So he got only delay, which is what we know. But actually, this is the other half of the story is negative time delay. So yeah, so it is minus 1.46, and the moon clock will measure plus a delay plus 0.26 nanosecond, which is far less than the negative one. Okay, so these factors can be used to do some technical calculations. That's all. So that's all. Thank you very much.
Okay, good. So we'll be having some questions. I think in the chat box, I can start with the chat box. I see one question by Tanushri Roy, right? And she asked whether this will the Shapiro effect be observable in any other modified gravity theories besides the bumblebee gravity?
Absolutely, absolutely. Of course, if you have any metric, it could be spinning, it could be static. You can do the simple calculation like in textbook and calculate the Shapiro delay or even time advancement, as we have mentioned here. It's the same. It is just the proper time effect, nothing more. It is just less than a classroom exercise.
And did you, mention, I think this this has no correlation with the gravitational redshift, is it?
Well, gravitational redshift is a good question. Gravitational redshift has to do with two clocks, right? Like in a Pound-Repka experiment, for instance. You have two clocks, okay? You compare the readings of two clocks. But here, only one clock is involved. Either the Earth.
Right. So there is no question of any gravitational redshift, right?
No, it is proper time. You see, when you measure proper time, this is all that you can measure. You don't talk about coordinate time, etc. You do not say that, oh, it is related to the coordinate time. By chance, we cannot measure. It is not the thing. The time that we can measure in the gravitational field is always proper time. So we do not make any other, it's just the proper time. We do not even say proper time effect because the time is the proper time. Because you cannot measure, you cannot measure any other time. And one clock, remember, either on Earth or on one clock. No comparison.
So do we expect the similar results from the radar-echo delay experiments or like that?
This is radar-echo delay. Shapiro delay is just the radar-echo delay.
Radar-echo delay experiment,
Yes.
So good, then do we have other questions from the participants? They're free to ask the questions. Most welcome.
I think there is a chat box, one question. Somebody asked, what happens when some modified gravity, this bumblebee?
I already discussed that question. In fact,
my question, I want to ask one question.
Please go on.
Bolo.
Actually, this bumblebee gravity, in this case, the black hole solution, does it require the anisotropic fluid? Just like somebody has taken this to describe the accelerating phase of the universe.
Yes, actually, it is easy to calculate the stress energy tensor corresponding to this metric. It is not difficult. And yes, of course, it will be anisotropic. This is my guess, but I can refer to you some papers where you have all these things have been done, because you have the metric, which I have not, the action and the field equations, which I have not shown here because of it will be very lengthy. So I didn't show it, but yes, it will be, there will be some anisotropic fluid as a source of this. Yes, should be. And of course, it is a classical solution with the lag in quantum gravity, because people think that this L can be measured even for Cassini spacecraft experiment. It is just measuring Shapiro delay. And that L was, this was the limit on L. It was not bumblebee, but it is indirectly. So there are possibilities that maybe the bumblebee effect is altogether nonsense. It is possible. Maybe some other gravity theory is there. But what remains is the time advancement effect. It will remain, whether you have bumblebee gravity or any other gravity.
Yes.
Okay, great. So any other questions among the audience? And if they are not, then let me thank Professor Nandi again for such a brilliant talk full with the mathematical equations and all that. Probably we can look for some modified versions of gravity also, but then he
Yes.
said this has to be explained again. I mean, this is very important, a crucial aspect
Yes.
where you can make a distinction with the modified version of gravity. There is a question, why Lorentz symmetry breaking actually occur?
First of all, this is just a guess. You know, Kostelecki, this man, Kostelecki was the one who first, because it is a standard probe. You do not know the theory of quantum gravity, and you cannot study its predictions. So it is just a guess, a probe, that what if we break the Lorentz symmetry? As I explained, that breaking Lorentz symmetry is not something great. You know, you can do it without really hurting or sacrificing the successes of special relativity. It is just a matter of synchronization convention that differentiates between Lorentz invariance and Lorentz non-invariance. It's just a mere convention, so you can sacrifice it. So your special relativity successes will be there, everything will be there, but Lorentz invariance will be gone. Now this is a probe that what if, since general theory of relativity cannot be accommodated within a quantum gravity framework, probably the hindrance is Lorentz symmetry. So break it. If you break the Lorentz symmetry, maybe you can match them together. Okay, this is a hope, a guess. I don't say that, and nobody says that this is the theory. But you can measure its effects within the laboratory scale energy. You cannot have Planck energy 10 to the 19 GeV. You cannot have, but you can have. Hi, Rasada. You can have ordinary laboratory energy.
Low energy violations.
Low energy, right?
Yeah.
Yeah. So you can start to sense the feelings of quantum gravity effects.
Right.
That's right. So this is just a probe. You know, it is not the final theory.
That is a very important probe, in fact.
Yes.
So to say.
So standard probe. But the main point was this gravitational time advancement. It is a negative time delay. So the distance to the moon is less than what we know it to be. That's the idea.
That's nice. So that answers the question. I think there are no questions. And therefore, we should thank Professor Nandi for such a nice talk. Right? And we should express our applause for his presentation at such a distance where he's sitting rather in the hot waters in Moscow, who is on the boring side.
Yes.
I all wish you a very safe stay, safe and delighted.
Oh, thank you very much.
I also settle down. Yeah.
I also like to introduce you to my colleague.
Oh, sure. Oh, great.
He has a contribution into this.
Okay, great. So we are lucky to see
to our university in India, in fact, because he was there.
Very nice to meet.
We wish you good health and very safe stay, all over, although these phases are of turmoil and disorder. But among the disorder, I mean, among all this time, you have picked up your time and given this talk. So
thank you very much indeed.
Thank you very much, Professor Nandi.
Thank you.
And let's move on further with our next talk, which will be given by Professor.
Bye-bye.
Okay. by Professor Dipankar Bhattacharya, who is our next speaker. I think he's here. Vikash?
Yes, I'm here.
Okay, great.
Yes,
So,
Professor Bhattacharya is
so
here.
he's looking nice, great from Ayuka, I think, from his office.
Yes, I'm in my office.
Okay, so Professor Dipankar Bhattacharya is in high energy astrophysics, and he has worked a lot on this neutron stars and all the cataclysmic events, in fact, gamma ray bursts and supernova and all that. Currently, he's a professor at the Inter-University Center for Astronomy and Astrophysics, and has been a scientist at the Raman Research Institute before, and he's won a number of awards and, of course, all applauses from different nooks and corners of the world. Professor Bhattacharya is also very intimately connected with this AstroSat project. We had our first talk by Professor Kanak Saha on the AstroSat, this ultra deep field, and Professor Dipankar Bhattacharya would be talking more about it. I mean, science from that we obtained from this AstroSat, and he would also be talking about the compact objects. So over to Professor Dipankar Bhattacharya for this nice talk. Hopefully nice talk.
Hopefully, yes.
Okay.
I hope you enjoy it. Thank you very much. It is going to be a talk which will be very different in nature from the one we just heard. Because, I thought I will just give you a glimpse of a very extensive set of results that are coming out very recently from the AstroSat mission on compact objects. And AstroSat is working on many other areas as well. But I would like to concentrate on compact objects. I'll just give you a feel for many of the results. So obviously it is not possible for me to present each of the results in detail. So I'll just highlight a few and then give you a sort of list of things that people are doing. So let me share my screen. Okay, there is some issue here. Student preferences. Allow me a minute. There is a.
Yeah, please go ahead. Take your time.
Yeah, it's not allowing to share, so I will have to.
Sir, please unmute.
We can see the screen now, I think. Yes.
Okay. Is
Yeah.
it visible now and you can hear me? Okay. Thanks. All right. So let me begin. So as I said that I would like to just give you a roundup on some results on compact objects with astrosat. So those who are electron volt to 800 kilo electron volts, that is a enormous range of photon energies that can be detected simultaneously in this mission, and that is one of its unique characteristics. The mission is flying at 650 kilometers altitude from the surface of the Earth, so nearly circular orbit with 6-degree inclination with respect to the equator. This mission has been put together by contributions from a large number of institutions, the primary ones being ISRO, Tata Institute of Fundamental Research, Indian Institute of Astrophysics, IUCAA, Physical Research Laboratory, Raman Research Institute, and the two international partners, Canadian Space Agency and the University of Leicester. And this has been now extensively used by people not only within India, but also abroad. About 50% of the users are from India, and over 50% is used by people abroad. So today's topic that I'll be dealing with is compact objects. So a quick introduction to compact objects. These are primarily end states of stellar evolution from relatively low mass stars, which leave white dwarfs as their final remnant. So there, white dwarfs can be found in the galaxy within a mass range of about 1/100th of a solar mass to about 1.4 times the mass of the sun. These very low mass white dwarfs can only be generated in binary systems when the mass is taken away from the progenitor star onto the other star. Otherwise, the single star evolution would leave white dwarfs not less than about 0.4 solar mass today. Anything below that has been processed in binary system. The typical radius of a white dwarf of about 1 solar mass is about 10,000 kilometers, so roughly about the size of the Earth. And the characteristics time scale associated with this white dwarf, for example, if the white dwarf oscillates, or if gravitationally bound object is orbiting the white dwarf close to its surface, those timescales are of the order of a second in case of a white dwarf. And the magnetic fields that the white dwarfs exhibit can go from low values to up to about several megagauss. Remember, the average magnetic field of the Earth is about a Gauss. So this is about 1,000,000 times stronger. If the progenitor star happens to be more massive, then it leaves heavier remnants, and those remnants could be neutron stars. The neutron star masses that we see are in the range of about 1.2 to 2.5 times the mass of the sun. Neutron stars have typical radii of about 10 kilometers. So these are a solar mass object squeezed within 10 kilometers. So so the densities are extreme. Densities are extreme, close to the density inside an atomic nucleus, and it exceeds it towards the center of the neutron star. And the typical time scales, which were about seconds in case of white dwarfs, is about milliseconds in this case. And neutron stars also harbor the strongest known magnetic fields in the universe. The typical magnetic fields measured on neutron stars go from about 10 to the power of 8 Gauss to about 10 to the power of 15 Gauss. If the remnant is even heavier, then the nuclear forces which hold the neutron star up against gravity are not sufficient. So since the support against gravity fails, the object can get squeezed into a black hole. So a black hole is a singularity surrounded by a horizon. Masses of such objects are higher than about 2.5 solar mass, because below that mass you could still get support as a neutron star element. But if you go above that, you create black holes. The black holes have a horizon size which is about 3 kilometers per 1 solar mass, and it scales proportional to mass. And the typical time scales also scale proportional to mass. So a millisecond times the solar mass of the black hole. Now, stellar mass black holes that have been found in the galaxy exhibit masses all the way up to about 10-20 solar masses. Then we have now found via detection of gravitational waves stellar mass black holes all the way up to 60 to 80 solar masses. And then at the centers of galaxies, supermassive black holes can be found, which go from about 1 million to about 1 billion solar masses. So black holes have a very wide range of masses. Now, the general property of compact stars or compact objects, I wouldn't call the supermassive black holes as compact stars, whereas these are. So under the umbrella of compact objects, I will combine white dwarfs, neutron stars, and black holes of all masses. So they exhibit extreme gravity. They also exhibit emission, which have high photon energies. So X-rays, gamma rays, and so on. Because the characteristic time scales of or around that object is very small, the intensity variations that you find from these objects can also be very fast. So they exhibit fast variability. And very often, such objects also exhibit outflows, particularly if matter is falling into it from some nearby object, then part of that matter which is falling in can be ejected at a very high speed. So it could be jet-like or less collimated, but outflows are quite common. The radiation received from compact objects are generated either at the surface, for example, in case of white dwarfs and neutron stars. So hot surface can produce detectable emission at high energies. Or in many cases, you see magnetospheric emission because you have a strong magnetic field and these objects spin, and a spinning magnet can produce a lot of voltage, and this voltage can accelerate charged particles, and those accelerated charged particles can radiate. So magnetospheric emission is also quite ubiquitous in compact objects, particularly with magnetic fields, their own magnetic fields. Black holes cannot harbor its own magnetic field, but the material around black hole can have its magnetic field. So surface emission and magnetospheric emission are commonly seen in white dwarfs and neutron stars. And all of these compact objects shine brightly when matter from either another donor object nearby or ambient matter from the surroundings fall onto them and get hot and produce emission. So for example, if you have a compact object, it could be either a white dwarf or a neutron star or a black hole, and if there is a star nearby, the gravity of this compact object can pull matter from the star, and this matter can then spiral into the compact object, coming in a disk form. So this is called accretion disk. And as it approaches the compact star, it gets hotter and hotter, and the Keplerian motion gets faster and faster. In this animation, what is shown is a neutron star with a strong magnetic field interacting with this disk, and this fast spin of the matter in the Keplerian disk can transfer its angular momentum to the neutron star and also speed it up to very short periods, up to millisecond periods. So the highest disk temperature, because matter keeps getting hotter as it approaches the compact object, is seen from the inner edge of the disk. And also the fastest time variability corresponds to the inner edge of the disk. So if you want to see high energy emission, then you will see it from the inner edge of the disk, and that will be variable at fast time scales. So to probe the inner accretion flow, you need to be able to measure this fast variability and do spectroscopy at high energies, for example, at hard X-rays. If the compact object is a black hole, for example, then the disk in principle can extend all the way up to what is called an innermost stable circular orbit, or ISCO. Now there could be situations where thermal processes take place here and then push the disk away from ISCO. But innermost stable circular orbit is the orbit around a black hole, which is about 3 times the size of the horizon of a celestial black hole, after which circular orbits can exist, and therefore a circular spinning disk can exist. The size of that innermost stable circular orbit for a non-rotating object is about 3 times the horizon size. But if the black hole is spinning, then the innermost stable circular orbit can come closer to the black hole. So the radius of the innermost stable circular orbit is a function of mass and angular momentum. And if one finds the size of the innermost stable circular orbit, it can allow you to constrain the values of mass and angular momentum of the black hole. In case of white dwarfs or neutron stars, the disk radius could be truncated by the surface. So disk can extend all the way to the surface of the neutron star, and it will be truncated there on the surface of the white dwarf. So that will decide what is the inner edge. Or it can be truncated by the magnetic field, like shown in this animation. Because it interacts with a strong magnetic field, and then the disk flow gets disrupted. So then the magnetic field will truncate the accretion disk. And in all cases, if there is a hot inner flow, so the disk flow gets increasingly hot as it approaches the compact object, and at some point it may get so hot that it will produce a corona, which can then push the disk away. So, so inner disk radius can be variable. The closest it can get is innermost stable circular orbit, or it can be truncated by these other means. So, as both seen in this animation and in this diagram here, from the inner part of the flow, you may often get matter being pushed out in collimated fashion, producing jets or outflows. So to study compact objects, we must have means to be able to detect radiation from all these different components, and to be able to identify those components. And to be able to identify those components, one of the tools is the variability of intensity. So because the variability of intensity will encode the local time scale, and since the local time scale of all of these compact objects could be very, very short. For white dwarfs, it is about seconds, but for black holes or neutron stars, it will be in milliseconds. So you need some measuring instrument which can detect such fast variability. And this is where the AstroSat's particular strength lies. It is able to do detailed study of intensity variation of sources across a large waveband with simultaneous spectroscopy of the order of 2 eV to 100 kiloelectron volts. And then in all wavebands, AstroSat records individual photons. And recording individual photons is the most versatile mode of observing. For example, to get an image out of an individual photon recording, you just make a histogram of the locations of the detected photons on your detector, and that gives you an image. If you want time variability, you bin these photons in time and you get a light curve, and from that you can notice the temporal variation in intensity. If you want a spectrum, you again bin the same photons in the photon energy, and the result that you would get is a spectrum. So the individual photons recorded with the position in the detector, the time of arrival, and the energy of the photon is a most versatile observing mode which AstroSat has adopted. And as a result, particularly for compact object studies, it has become a very powerful instrument. And the third property of this mission, which is also very useful for compact object studies, is the ability to measure polarization at hard X-rays. This is above 100 kilo electron volt, all the way going up to about 500 kilo electron volts. This plot compares the wavelength coverage and time resolution that AstroSat has with several other observatories and instruments which are currently available. And what is shown in red are AstroSat, and these other colors are other different instruments. So as you can see, AstroSat has one of the largest wavelength coverages among all these different instruments. And not only that, particularly at high energies, AstroSat has among the best time resolution. The time resolution of AstroSat in both the LaxPC and the CZTI instruments are sub-millisecond. This is 10 microsecond and this is 20 microsecond. Only a couple of instruments better this, that is NuSTAR and NISA, which are also very important instruments to study compact objects. So no surprise then that if we look at for the last 6 years, what kind of object AstroSat has spent its time observing, the largest chunk is taken by compact stars, and the next largest chunk is taken by active galaxies. Both these are will fall in the category of compact objects. These are supermassive black holes, and these are stellar mass objects. So compact objects, these two together, take up the largest fraction of AstroSat time, and they continue to do so today because this satellite is really particularly suited to this kind of objects. And we are now beginning to see a whole lot of results coming out of all the observations that have been taken. And in what follows, I will just describe a few of those. So let's start with white dwarfs. I'll just highlight 2 pieces of result. One is discovery of very low mass white dwarfs, extremely low mass white dwarfs, less than 0.2 solar mass. So they have been discovered using ultraviolet band as companions of stars in open clusters. So the ultraviolet detector on AstroSat allows one to make this, construct this spectral energy distribution of stars that you observe. And for example, in this open cluster, here is a particular star where this green line shows you the total observed spectrum. But if you look at the star itself and look at its own predicted spectrum, then it is shown in this orange line. So at shorter wavelengths, you see that there is a deficit of emission in the model compared to what is observed. And this difference then allows one to detect the presence of a companion which fills in the missing emission. And this emission is characteristic of a very low mass white dwarf. And so there are several such stars for which this has now been done, and in fairly large number of low mass white dwarfs have been discovered by AstroSat this way. Another white dwarf result that I would like to mention here is a recurrent nova, V3890 Sagittarius. So these are white dwarfs which accrete matter, and once in a while the accreted matter gets, there is enough matter accumulates so that it gets hot enough to ignite hydrogen, and so the hydrogen ignites and nuclear fusion occurs, and a lot of heat is generated very quickly. A lot of matter is then ejected from the surface, and this is called a nova explosion. And this particular object shows this nova explosion periodically in several years of time scale. And what AstroSat has observed now is, after this outburst, then the object intensity decays, and as the intensity decays, the spectrum also changes, and the spectrum changes to something which we call super soft state. So super soft sources are a class of sources which were thought to be white dwarfs which steadily accrete matter and then burn hydrogen steadily at its surface. But this observation shows that even after a nova explosion, there could be a little period for which a white dwarf can look like a super soft source. So this is also a new discovery. This is made with a whole slew of instruments, including AstroSat, optical telescope. So these are the kind of work that are coming out of AstroSat observations now for white dwarfs. Going to neutron stars, where there is a lot more activity with AstroSat. So let me start with magnetospheric emission. One of the strongest magnetospheric emitters that you can see with AstroSat is the Crab pulsar. It's a fast spinning pulsar, 33 millisecond spin period, very strongly magnetized over a teragauss magnetic field. It is an isolated neutron star. It doesn't have a binary companion. So with AstroSat, we are able to find its pulse period and construct its pulse profile at all the wavebands that AstroSat observes in, starting with ultraviolet, going through soft X-rays, then hard X-rays, and then to very hard X-rays up to 380 kilo electron volts seen over here. And you can see that the pulse profile shape changes with energy. At lower energies, the first peak dominates, at the higher energies, the second peak dominates. One of the things that AstroSat could do was to measure the polarization at 100 to 380 keV band of the Crab pulsar envelope. And what is plotted here in these two diagrams are, as a function of pulse phase, the polarization vectors as projected in the sky, with this white line showing the projection of the spin axis of the pulsar. So you will see that the polarization vectors are all tightly clustered around the spin axis. So that means the high energy emission that we see from the Crab pulsar, the polarization vector of this high energy emission is practically parallel to the spin axis of the pulsar. And this is going to be a bit of a surprise if the high energy emission originated close to the neutron star surface, where the magnetic field bends by a large amount as the pulsar rotates, and we see different parts of the magnetosphere. And in case of synchrotron emission, which typically gives rise to this high energy emission, the polarization is supposed to be perpendicular to the projected magnetic field. And if the projected magnetic field is changing direction, then one would expect a significant change in the direction of plane of polarization as the pulsar rotates. So this observation tells us that the high energy emission that we see primarily does not come from the inner magnetosphere, but comes from the wind zone, where outside in the outer part of the magnetosphere, you have the magnetic field line sort of confined in equatorial plane, and they spiral out. And in that region, the magnetic field is almost completely perpendicular to the spin axis. So the polarization of synchrotron emission produced there would be perpendicular to the local magnetic field, which will be parallel to the spin axis. So this observation practically nails down the emission zone of where this high energy emission originates. Now we have also detected about dozen pulsars above 100 kiloelectron volts with AstroSat, which are much weaker. So we cannot do such detailed study for those, but at least we are able to detect, and we should be able to make spectroscopic studies of these high energy pulsars. Going to accreting neutron stars, we will look at accreting neutron stars in two different classes. One in which the donor star, the star companion star which is donating mass to the neutron star, is high mass, and by high mass one means several times the solar mass, maybe 5 to 10 times the mass of the sun, or even larger. So in these cases, since these high mass stars are short-lived, so the neutron star also is relatively young, and for these neutron stars magnetic field is high, and as the neutron star accretes matter, the matter is channeled by the strong magnetic field onto its poles, and that channeled matter emits X-rays. If you take a spectroscopy, X-ray spectroscopy of such a neutron star, then often you would see over and above the continuum that describes the spectrum, there is a absorption feature which stands out. If you, for example, fit this only with continuum model, then there will be a residual of this kind which will stand out. And then if you then fit a line feature here, then the residual will be flat. There will be no significant residual left. So this line feature is called cyclotron line, is a cyclotron resonance scattering feature. And this cyclotron resonance is caused by electrons which are gyrating in the local magnetic field and are stuck to basically the lowest Landau level. And as they move from one Landau level to another, it absorbs radiation or scatters radiation, and that causes the reduction in intensity at that wavelength, and that gives you this line. So this line frequency is strongly tied to the magnetic field strength. For 10 to the power 12 Gauss magnetic field, the cyclotron energy would be 12 kiloelectron volts. So it is proportional to the magnetic field. So therefore, once we measure the energy of this line, we are actually measuring the magnetic field in the emission region. And in this case, you can see that the line energy is about 20 kiloelectron volts. So that gives you a local magnetic field about 1.5 times the, or 1.8 times the times 10 to the power 12 Gauss. So this kind of cyclotron resonance scattering features have now been detected by AstroSat in several neutron stars, going all the way from 5 kiloelectron volts to highest to about 50 kiloelectron volts. So there is a whole range of magnetic fields that you can measure using this. One particular object has been very curious because over time this object has been studied by many missions, and its cyclotron line energies appears to be coming down with time. And this is Hercules X1. So people have speculated that its magnetic field is decaying over a few years. So this object also has been studied within AstroSat, and then all the data from all other missions also put together. And then what one has found that is that the cyclotron line energy correlates with the intensity that you see of the neutron star. So therefore, at times when the X-ray intensity is low, you expect low cyclotron line energy, even if the magnetic field is stable. So once that is taken into account, then this observed behavior of cyclotron line can be modeled by having initially a little bit of a reduction and then being flat over time. And this is a new result, which has now also been confirmed by a few other groups from other instruments. But so this result then says that there is a process that is going on near the surface, which is probably screening part of the magnetic field. And then having screened up to an extent, then the screening doesn't work anymore. So field stabilizes at that value. There are other properties of these neutron stars which have been observed and detected with AstroSat. Timing has been performed, pulse detection has been done, spin and orbital period measurements have been carried out, quasi-periodic oscillations have been seen, and continuum spectra have been observed for a whole lot of neutron stars, as they have listed here and reported in a large number of papers. For this object, AstroSat also detected a highly ionized absorber around this system, which was not known before. And then a couple of objects of exotic variety have also been observed in this category. They are called ultraluminous X-ray pulsars, one in the Magellanic Bridge and one in the Milky Way. The other set of accreting neutron stars are where the companion star has a low mass, typically even lower mass than the mass of the neutron star. So in this case, the neutron stars that are found to be there have fairly low magnetic field. So the disk can practically extend all the way to the surface of the neutron star. And the time scales of oscillation, intensity variation, and so on can become very short. And this rapid spectral and intensity variations can be studied very well with AstroSat. Matter falling onto the neutron star can accumulate and from time to time undergo thermonuclear fusion. And when the thermonuclear fusion gets triggered, you see a thermonuclear burst. So those have also been observed with AstroSat. High frequency, about 830 hertz quasi-periodic oscillation has been seen from this object 1728-34. And not only that, in this object, X-ray bursts have been seen as well. And within the burst, coherent oscillations, actual pulsations have been seen at 380 hertz, which actually corresponds to the spin period of the neutron star. Then lower frequency quasi-periodic oscillations and correlated spectral and timing behavior has been seen in several sources. The different parts of the spectrum, energy spectrum, vary in different ways, and time lags between different parts of the spectrum can also tell us something about where the emission is originating and the structure. The structure of the corona have been deduced from such time lags. Millisecond pulsations have been observed. And in X-ray bursts, one of the interesting things that has been seen is the persistent emission rises after the burst. So once the burst is over, the level of emission does not return to the pre-burst level, but stays a little higher. And this persistent and hence some extra emission is seen for a while after the burst. And this again is seen for the first time with AstroSat. Another discovery was bursts which occur in very rapid succession. Here is an object 41636-536, which is known to burst at fairly close intervals, but this is an extremely close interval. 3 rapid bursts. It's a rare triple which have been seen, and this is also an AstroSat discovery. Here again, burst oscillations at 581 hertz have been seen, so that gives you the spin period of the object. Time resolved spectroscopy has been done. There is another neutron star Cygnus X2 where 5 new bursts have been detected, and bursts and dips have been detected in this object 1323-62. I will show you something about Cygnus X2, which is interesting. This is a very recent paper from people working in Mizoram, and it's also one of the first observational astronomy papers that have been published from Mizoram University. And you can, what they detected was this quasi-periodic oscillation in the power spectrum of Cygnus X2. This is frequency times power, and this is frequency. And this power spectrum showed this quasi-periodic oscillation, and also this noise bump. Now, if you look at the spectral lag of these two features, so as a function of energy, the quasi-periodic oscillation has a positive spectral lag, and the bump has a negative spectral lag. Now, positive spectral lag means the higher energy emission appears later. Soft lag means lower energy emission appears later. So this tells us that in case of this feature, higher energy emission comes later because there is a Comptonization process going on. So Compton scattering takes time. So as Compton scattering makes the photon energy higher and higher, it takes correspondingly larger amount of time, and therefore the high energy emission comes later. So this is a signature of Comptonization. Whereas in this case, you have low energy emission coming later. So this could probably be coming from the disk. For example, an oscillation originating in the corona can then get reprocessed by the disk. And since the corona produces higher energy emission, and the reprocessing, of course, the disk emission has to travel to the disk and then get reprocessed. So that takes time. So in that case, you would expect the soft emission to be delayed. So very interestingly, this feature shows soft lag, this feature shows hard lag. So from there, you can conclude that this feature probably comes is processed by the corona, whereas this is has more to do with the disk. Just from the basis of spectrum alone or the power spectrum alone, you would not be able to tell this. So this is one of the strengths of astrosat observations, and this technique has been now applied to many sources. There's another neutron star anomalous extra binary. Again, it shows this kind of peak noise, and people have studied the correlation of this peak noise with various properties like temperature, Compton optical depth, noise flux, and so on and so forth. This is just an example, but it has been done for other sources as well. So coming to accreting black holes, one knows in this picture I showed before that there are several components: the disk, the corona, the jet, and so on. And people often observe highly variable X-ray emission from here, quasi-periodic oscillations, broadband noise, and in the noise you have break frequencies like the peak noise I showed. Then there are spectral state transitions, where the source may go from a state like this, where there is very little of this high energy emitting corona, and then you can have a corona appear when the source will become hard, and this will get pushed out. So the soft emission will, so this part of the emission will, disk emission will decline. So such state transitions have been seen, and spectrotemporal behavior actually depends on the black hole mass and spin and accretion flow properties as well as the spectral state. Many of these sources are transients, they are not seen all the time. So occasional large outbursts happen, and as soon as the outbursts happen, then people rush to observe it. And for that, AstroSat has a mode called the target of opportunity observation. And this has been applied to these black hole sources, many of these black hole sources, and a lot of things have been done. This is one of the steady black hole sources, GRS 1915 plus 105. It is available all the time, but just now, just some year or so ago, its intensity has declined. So this is an observation from LAXPC, Sky Monitor, just to show you the kind of observation light curves that you can produce. So Here is a state transition, which was seen in a black hole X2 binary Cygnus X3. A spectrum went from this state to a state where you saw a large high energy tail, and this was accompanied by a giant radio flare. And then it went to a flaring soft state where the spectral shape changed. And this excess emission seen in this tail is from the base of the jet, which produced also the radio emission. Then spectroscopy, sometimes including Chandra, sometimes just with astrosat alone, can give you a very good idea of the temperature distribution of the emitting region that produces the emission from these sources. And that gives you a good idea of where the inner accretion disk is. And as I have said, this location of the inner accretion disk gives you an idea of the mass and the spin of the black hole. And in this case, one could constrain that the spin is very high, between 0.9 to 0.94 times the maximum possible spin of this black hole. This is an example of the broadband power spectrum, where you see this broadband noise, and you can see that this broadband noise is energy dependent. So this is the noise power spectrum at 3 to 10 keV, noise power spectrum at 20 to 40 keV. So there is a change in the shape of the power spectrum, as well as there are spectral lags. As I have said, as a function of frequency, the intensity variations have a different delay. As a function of energy, the delay profile changes. So that has been studied in various sources and fitted with the fluctuation propagation model from outside to inside, like the stochastic propagation model. This source has also been seen in extreme soft state. There are special properties there which have been reported now. This source, which I showed in the previous slide, GRS 1915 plus 105, has been studied in all of its spectral states, and it shows various different kinds of power spectra, sometimes with quasi-periodic oscillations, low frequency quasi-periodic oscillation, high frequency quasi-periodic oscillation, and so forth, going all the way to 70 hertz. So quasi-periodic oscillations can go all the way to 70 hertz in this source. So this has been studied extensively by many people in a number of papers, reporting time resolved spectroscopy, accretion flow evolution, quasi-periodic oscillation, inferring mass and spin from high frequency QPO, then finding the truncated accretion disk, variable frequency, high frequency QPO, and so on. So studies of this kind have now been done for a number of black hole sources, which I have listed here, and similar conclusions have been derived in many of these cases. A large fraction of these are transients. So these sources were followed up when the source just became bright and became visible, and stayed visible for some time and then disappeared. So many of these objects are such target of opportunity observations. Many of these reports are from this target of opportunity observations. So here is an example for GRS 1915 plus 105. You have different quasi-periodic oscillations. Some show soft lag, and some show hard lag. Soft lag showing reprocessing, hard lag showing optimization, as I have mentioned already. And the QPO frequency becomes also a function of the luminosity. This correlation is seen in this object, as well as QPO frequency correlating with other properties of spectrum. For example, here in this particular case, Maxi 1535 minus 571, the QPO frequencies correlates very strongly with the slope of the spectrum, not so much the intensity of the spectrum. And this also gives us a handle on where the QPO originates and the nature of the Comptonizing cloud. Here is one of the recent papers on GX339-4, another of such transient black holes. When it was bright, observations were taken, and this power spectrum has these multiple spectral bumps. This is called a break, and this break frequency again is found to be correlated with the intensity that we get from this object. And here is a one such transient source, which showed not only the standard light curve, but periodic set of dips in intensity in this light curve, dips of 7 hours. And this has been attributed to some absorbing material sitting at the outer edge of the accretion disk, which is undergoing Keplerian motion around the black hole with the 7-hour period, and it is absorbing the X-ray radiation when it comes in between us and the black hole in our line of sight. This source also shows quasi-periodic oscillations and shows the lags. The 3 quasi-periodic oscillation peaks have been seen. Their lags are different as a function of energy. And using all this information together, people have been able to put a constraint on a strong constraint on the black hole mass between 11 to 14 times the mass of the sun. Now, another way of constraining mass and spin of black holes was measuring these characteristic frequencies in the power spectrum and subjecting them to this relativistic precession model, where these 3 different frequencies correspond to the periastron precessing frequency of an orbit, then the nodal precession frequency of an orbit, and the orbital frequency in the orbit. So the relativistic precession model predicts these 3 frequencies, how they will behave as a function of nodal frequency. Now, in this particular source, this work has been done, taking these characteristic frequencies and plotting them, and they fall on the expected lines from the model. The parameters here are the mass and spin. The mass of this object is relatively well known from other measurements, starting within, it is within about 8 to 10 solar mass. And using that prior, one can then constrain the spin very strongly in this case between 0.725 to about 0.775 of the maximum possible spin that the black hole can have. So this has been possible by applying this relativistic precession model. Now coming to supermassive black holes, one has these active galaxies which harbor the supermassive black holes. Various kinds of studies have been done with astrosat, including the change of their spectra with time, as well as the timing, power spectral breaks, which gives us some estimate of the mass of the supermassive black hole as well. Coming to the last thing that I want to mention is that astrosat is also a prolific detector of gamma ray bursts, and these gamma ray bursts occur when a compact object like a black hole is either formed, or 2 neutron stars merge, or a black hole merges with a neutron star. So in this diagram, there are 492 gamma ray bursts, their location in the sky that have been detected with astrosat are shown. And in these 2 colors, I basically distinguish between short gamma ray bursts and long gamma ray bursts. So short gamma ray bursts are attributed to the merger of compact objects. Long gamma ray bursts are attributed to the birth of black holes. So you can see that we have seen all over the sky objects of both kinds. One particular property of astrosat is to be able to measure polarization, and in 5 years, about 20 objects were bright enough to measure polarization, of which 5 have shown detectable polarization and 15 others strong upper limits. And this certainly puts some strong constraint on the way the radiation is generated in gamma ray bursts. I think I'll skip this. Coming to concluding remarks, astrosat is a powerful instrument for observing compact objects and their immediate surroundings. It has broken new grounds in spectral timing behavior of compact binaries, simultaneous broadband spectroscopy, and hard X-ray polarization measurements. And as I have shown, most of the observatory time is dedicated to compact objects. A large number of targets have been observed. A lot of this data is available for anyone to use. It's a public data available in the archive. we strongly encourage widespread use of these data. And new observing proposals can also be made. The current cycle is on for proposals until 10th of March. So if any one of you want to observe, make new observations, please do put in proposals by 10th of March. And target of opportunity observations can be proposed anytime when an object goes bright, like a black hole source comes up. One can propose target of opportunity observations. And if in any of these, either in proposing or in usage of data, you need any help, please do contact AstroSat Science Support Cell, which we run at IUCAA, which offers training and support to any interested user. Thank you very much.
Thank you, Professor Bhattacharya, for your nice and extraordinary talk, enlightening us with the recent discoveries of a dozen of X-ray pulsar by AstroSat. We are really thankful to you. Now, discussion is open among the participants. If there is any question or query. I have a question. Is there any research on determining the mass of the neutron star? Because there is a limiting mass around 2 solar mass. So is it possible to find out limit?
Mass measurement using X-ray observations is attempted through this X-ray burst spectroscopy.
Okay.
So because if you see what is called a photospheric radius expansion bursts, there you get a critical luminosity, which is the Eddington luminosity, at which the photosphere is lifted. The matter is pushed out because radiation pressure balances the gravity. So if we can measure that luminosity, we know what is the Eddington luminosity level. So then that correlates immediately with mass. So that is one way we can measure the mass of the neutron star. Also, there are other ways too. So, for example, if you really know that quasi-periodic oscillation is happening in an orbit which is hugging the neutron star, then the Keplerian frequency itself will tell you what is the mass of this mass contained within this radius. So that will also be a constraint on the mass of the neutron star. So both from timing as well as this burst spectroscopy, one can put constraints on the mass of the neutron star. Another thing that is used for putting constraints on neutron star mass is iron line. But to do that, one needs spectral resolution, which is better than what AstroSat has. So for that, other instruments like XMM or NuStar are better.
So our students are encouraged to use the AstroSat data. In that case,
there is a lot of data, so you don't even have to wait for your observation to be done.
You and other people.
Yeah, just retrieve data, and
yes,
phenomenal amount of science that can be extracted. I can tell you today that only about 25% of the data that has been collected have so far been published. Has any result been published from that? But any piece of data which is collected can produce not just one piece of result, but many types of results. So I would say from whatever has been published so far, there are at least 50 times that result waiting to be published. So please get active and please use it.
Thank you, Professor Bhattacharya, for your nice talk. Thank you.
Thank you very much for inviting me, and
thank you, Lord.
Thank you very much. Bye. I'll unshare.
We are moving to our last talk, last not by but the least. Professor Mark Trudin. Professor Mark Trudin is a theoretical cosmologist and particle physicist. He is the Fair and Eugene L. Langevin Professor of Physics and co-director of the Center of Particle Cosmologies at the University of Pennsylvania. He kindly accepted our invitation to give a talk. We are very thankful to you, sir. His main research interest is in quantum field theory, general relativity, and superstring theories. Basically, topological defects in supersymmetry also. He did some work that are very much interesting to our group. We are doing cosmology at North Bengal University, and we are eagerly waiting to listen from you. The topic is very nice. The many incarnations of dark energy, which is a burning topic of these days. So I request Professor Jordan for your lecture, please.
Thank you. Thank you for having me. I just need to figure out how to, I haven't used this Google Meet recently. How do I share my presentation?
At
Can you
the
hear me?
bottom of the screen, you
Yep.
see a set of icons. One is
I
a
just
box
present
with an
the
arrow.
entire screen. Got it. Thank you.
Yeah, that's right. Share the entire screen. That's it.
Let's make sure this works. How's that?
Yes.
Perfect.
Fine.
Okay, I can't see any of you anymore, so please speak up if there's something wrong or you have questions. Okay. You can hear me, yes?
Yes, we can hear you.
Okay, good. Well, thank you very much for having me. It's a pleasure to be here. This will be a different kind of talk. I think this will be a theory talk. I really enjoyed the part of the last talk that I saw, but this one will be a change of direction. I wasn't quite sure. The audience seems quite broad, so this talk has quite a lot of background material in it, but then some general things that I think are important to think about when thinking about dark energy, and it'll apply not only to dark energy, say, as applied to the accelerating universe, but also to things like early dark energy, although I don't think I will have time to talk about that today. So I'll talk a little bit about motivation, cosmic acceleration, why we're interested in topics like this, and I'll very briefly review some possible approaches, the cosmological constant, dynamical dark energy, modified gravity, and I'll try to present how you should, at least in my opinion, one should think about all these in the same way through a common effective field theory approach. And then I'll move on to what the theoretical issues are that face dynamical approaches to cosmic acceleration. And that will lead me to talk about screening mechanisms, which are a very clever way to evade many of the issues that face theoretical approaches to the accelerating universe. And that'll lead me to some sort of deep connections to particle physics and field theory. What I'd like to do eventually is talk about massive gravity as an example, but I think it's sort of too involved a discussion for a 1-hour talk. So instead, I'll talk about a class of scalar field theories that have many of the same features in common, which are called Galileans. I'll very briefly after that talk about how you test these theories, and I'll finish with a few comments. And if I had time, I would have an addendum at the end on early dark energy, but I'm pretty sure I won't have the time. The sort of overarching goal here is to try to explain a little bit how particle physicists think about constructing cosmological models in general. And I think something that's useful if students in particular are interested in the sort of basics of what I have to say is this review article we wrote quite some years ago now, where we talk about all the different aspects of what I'll talk about today. Okay, so just some background, things we all know, but just to get us on the same page. We look at the expanding universe. We try to construct a modern day Hubble diagram. And what we find is that this remarkable fact, which is now, almost a quarter century old, that not only is the universe expanding, getting larger over time, the cosmic derivative, but in fact, it is accelerating. The second derivative of the cosmic scale factor is positive. And that's something that was only possible by precision measurements, at least at first using type 1a supernovae, and later by using sort of concordance measurements of many different things in cosmology. Now, if you want to know as a cosmologist, why is the universe accelerating, which is the question that people like me care about, then we're used to addressing cosmological problems in the context of general relativity. And if we do that, if we trust general relativity, then there's a very simple relationship between the acceleration of the universe and certain properties of the mass energy contents of the universe, namely this acceleration equation that I've written here. So the acceleration is proportional to minus the sum of all the energy densities and 3 times their pressures of the things in the universe. And it's not so difficult to see, therefore, that if you want to have a positive acceleration, then the only way that can happen is that the universe is dominated by some sort of strange matter, strange stuff, which obeys the criterion that its pressure is negative, and not just negative, but sufficiently negative, less than minus 1/3 of its energy density. And anything of that kind, when people talk about dark energy, that's what they mean. Okay? They mean something that obeys that. So in cosmology, it's very typical to write the stuff of the universe in the form of an equation of state parameters. So if we write P is equal to W rho, then obviously the criterion I just wrote down translates to W less than minus 1/3. And then looking back at the data, you can ask, what does the data tell us? And here's just some data from the DES 2019 results. There are more modern results than this, of course, but things have not changed to the extent that I care about particularly. And these generally, depending on how you combine data sets from the microwave background, from large-scale structure, from supernovae, give you a W that is very close to -1, which would be a cosmological constant, but with some error bars around it indicating that it could be both greater than -1 or less than -1. And I've given the actual numbers from these collaboration results right here. Now, given that, many people think that the most simple explanation for the accelerating universe is the cosmological constant itself. And I won't talk a lot about that in this presentation, but it is worth certainly saying a few words about that. So what is the cosmological constant? Well, in a modern way of thinking about it, the vacuum is full of virtual particles that carry energy. And the equivalence principle, or if you like, Lorentz invariance, tells us that if you ask what the average energy momentum tensor of all those virtual fluctuations of the vacuum are, then it has to be proportional to the metric. And it takes this form that I've written here. And that is exactly what a constant vacuum energy would be. And in many ways, you would think that that's an exciting result. I mean, we have an observational result, the accelerating universe. And here we have something that exists in our particle physics theories, namely quantum fluctuations, and they give you something with the right form. The bad news, of course, is that if you do a sort of estimate of the size of these fluctuations, and the simplest thing one can do is just to take the standard model fields, which we know exist in the universe, treat them as a collection of independent harmonic oscillators and sum over their 0-point energies up to some cutoff, then even at the most conservative value of that cutoff, a TeV, so above the scale of current colliders or at the scale of current colliders, the difference between the theoretically predicted number and the number needed to explain the accelerating universe is at least 60 orders of magnitude. And that is, of course, as we all know, an enormous and entirely unsolved problem in fundamental physics. And it was there before we knew about the accelerating universe, and the accelerating universe has just made it a much more pressing problem to understand that. At this stage, how to solve this problem, how to predict a cosmological constant that has the right magnitude is not known. And not only that, it's sort of worse than we don't have any ideas. There's a fairly powerful no-go theorem due to Weinberg that anyone who has an idea about generating a small cosmological constant has to overcome. And many of the sort of simple and even not so simple things that one can imagine to dynamically adjust a cosmological constant to stay small and remain small run afoul of this no-go theorem typically. Now, there is one idea that I will spend very little time on because I don't like it very much, and that is that it could be that the cosmological constant, and therefore the current accelerating state of the universe, is a consequence of the anthropic principle. Okay. The notion here would be that something like string theory, for example, the string landscape has many, many vacua with many, many different values of the cosmological constant, and that eternal inflation populates those. And in different parts of the universe, the expansion happens in different ways. And then the argument would be that there's some probability for the universe to end up the way ours does. And the cosmological constant we have is the one that is big, but small enough to be consistent with the development of intelligent life to ask, why is there a small cosmological constant? If you're even going to start to think about this, you need to understand how to compute probabilities in spacetimes like this. There's no currently accepted answer about how to do that. There's a lot of serious work going on. I don't mean to denigrate that work. It's important. But for me, it's too early to know if we could make sense of this reasoning. And I don't find this a very compelling answer to the problem. One way to think of this is that it's a logical possibility, but it relies on a lot of assumptions. Okay, the interest in the anthropic solution of the cosmological constant relies on string theory, which may not be the correct theory. It requires on the string landscape, which may not be a feature of string theory. It relies on eternal inflation in the landscape, which might not work. And it relies on solving this probability measure problem, which we don't have yet. And that's a lot of steps to understand this. I'll also point out that if we do find a dynamical understanding of the cosmological constant, it would be very hard to then accept an anthropic explanation, even if we had thought that it was important before that. So I think that's another thing that should give us pause. So I won't dwell on this, but let me just say that I think it's worthwhile working on this idea, but I'm not working on it myself. So moving on, just a comment on model building in cosmology. We're 15 years, 25 years after the discovery of cosmic acceleration. At the beginning, when people were writing down models, it was the Wild West. Okay, but now, you know, it's a mature field and the bar for interesting ideas is quite high. And for people like me, questions of theoretical consistency and, of course, ultimately observational viability are key. So without a formulation, if one has an idea, without a formulation in which you can ask deep questions of theoretical consistency, I think the models are intrinsically less interesting. So I'll be focusing on that kinds of models and the issues they have in this talk. Yeah, so I'll just leave that there. Okay, so what could be the answer to the accelerating universe? Well, the first one is this thing I mentioned already, dynamical dark energy. The idea here is to say, okay, there's something in the universe that causes the universe to accelerate, that obeys W is less than -1/3, and we have to figure out what that could be. Okay, and it isn't enough just to write down perfect fluids. So I can't just write down a fluid that has P less than -1/3 rho, because that really isn't a fundamental description. And so the right way to think about these things, as far as we know, is through quantum field theory. So you write down a Lagrangian. Here I've written one for a scalar field with the potential, and you compute its energy momentum tensor. You, at least at this point in my talk, assume Einstein gravity. That energy momentum tensor sources Einstein gravity, and then you try to figure out the mathematical and physical consequences of a theory like this. We're going to assume that there's a principle that sets the vacuum energy to 0, okay? Because otherwise you'd be using your cosmological constant. Dark energy in this picture is very like inflation, but at the other end of time. Okay, inflation happens at early times, at high energies, and comes to an end so the universe can enter the Big Bang phase. Dark energy happens at low energies, late in the universe, and at least as far as we know at this point, has no real reason to end. It could dominate forever. Okay. So at inflation, a very useful way to write down dark energy was indeed these scalar fields. And so one can try to do that in cosmology. And one very simple example is what's called quintessence. One writes down a scalar field, gives it a potential, so it's rolling down in such a way that it accelerates the universe. And it does that if it has a small slope. So if you have something with a small slope, the equation of motion of such a field takes this form, the equation of state takes this form. And obviously, if phi dot squared is small compared to v, then this will approach -1, but will certainly be negative and less than -1/3 if you arrange things correctly. This is one very simple way that you might first think to get an accelerating universe. And people thought about this, in fact, even before the accelerating universe was discovered. Now, approaches like this have some issues and advantages, but they do have problems. Okay. So an idea like this requires, the problem we're trying to solve, the cosmological constant problem, or if you like, the dark energy problem, is a very extreme fine-tuning problem. Replacing that problem with a dynamical field, it comes along with its own extreme fine-tuning problem. You want a very flat potential and a very low mass scale. And in order to, whenever you write down a theory with an artificially low mass scale and artificially flat potential, you face the problem of technical naturalness. Okay. In other words, quantum mechanical fluctuations in your theory will correct the potential in such a way to ruin the nice low scale and flat behavior that you've arranged. One way to tackle this is to introduce some symmetry. For example, make your quintessence field a pseudo-Goldstone boson, which I'll mention again in a minute. But even if you can do that, there are other fascinating constraints on theories like this. For example, we learned from field theory that if you write down a light field, it should couple to other fields in the universe. For example, it should have derivative couplings to the standard model. And it turns out that if you do that, then polarized radio light from distant galaxies can be rotated by the presence of this field. And that turns out to actually constrain quintessence fields quite strongly. On the other hand, if one can solve these problems, there are models out there, some quite exotic behavior, like exotic kinetic terms, like KSMs, that have advantages that go way beyond solving fine-tuning. For example, they can try to address the coincidence problem of dark energy. Why does the universe accelerate now as opposed to at some other epoch? And so there can be real advantages of an approach like this. But at present, there are no really compelling models. I'm just trying to describe the issues associated with constructing them. Now, there is another possibility. Everything I've said so far is that you're looking for something that you plug into the right-hand side of Einstein's equations and drives the accelerating expansion of the universe. But I'll point out that we don't really measure the equation of state of dark energy from cosmological observations. What we really do is we infer it from the Hubble plot. So very simply speaking, one can take Einstein's equations, put in some dark energy, invert the equations and write it in terms of the equation of state. And if you do that for a flat universe, you'll end up with something that looks like this. Omega matter is the fraction of the density of the universe that is in regular matter plus dark matter, and h dot is the derivative of the Hubble parameter h. So, of course, it could be that maybe gravity is modified, right? Maybe the way in which the Hubble parameter or the scale factor is related to the matter content of the universe is not the one you use to write down this equation. And then the thing you would infer from this equation, the W effective, by measuring h dot, is maybe not related to the actual values that are relevant for the energy sources you've introduced. So just to give a very simple example, if the universe were described by a Brans-Dicke theory, so a different theory of gravity, here I've got a scalar tensor theory with strange couplings between the scalar and the Ricci scalar, then you can write down, I'm not selling you this, by the way, as a great model, it's a proof of principle. Turns out you can write down a model of this with this parameter omega that's I've written in here, large enough to satisfy the tightest constraints on Brans-Dicke theories that come from the Cassini mission. And in a paper that we wrote a long time ago now, we showed that you can actually infer, for example, W is less than -1, even though there are no energy conditions violated in your model. So we can kind of decouple the microphysics that you think you're measuring from the cosmological observations because gravity isn't quite what you thought it was. So reasoning like this can sort of lead you down the path to thinking, well, how much do I really rely on general relativity when it comes to inferring the stuff of the universe? And of course, a related tale to this played out over a 50-year period, over a century ago, when people were trying to figure out how Mercury went around the sun. Mercury, as we know, goes around the sun in a precessing ellipse. This is very exaggerated, of course, here. And Newton's laws would tell you that it should just go round in an ellipse. It should not precess. And at the time, of course, Leverrier who had had great success with this kind of reasoning earlier, came along and said, oh, well, this is due to some sort of dark matter or dark energy. He didn't use those words, of course. He said, well, there's probably another planet on the other side of the sun. They called it Vulcan. And we don't see it. It's dark because the sun's in the way. But its gravitational effect is such to tweak the behavior of Mercury and make it precess around the sun. And so what he's saying there is we have a theory of gravity, Newton's theory. It works well. We've got an observation that doesn't seem to gel with that, but that probably just means we're missing some matter that we haven't taken into account. And we all know that this was not the answer, okay? The answer, in fact, was Einstein came along and said, no, in fact, all the matter you needed was right there, the sun and Mercury and the other planets, which are not so relevant to this. And in fact, what you need is a new theory of gravity. And the difference between the new theory and the old theory when it comes to this orbit is precisely just enough to explain this secular rotation. So, thinking about the problem of the accelerating universe, one could take this point of view and ask the question, could a similar story to this be unfolding today, such that cosmic acceleration is sort of the canary in the mine that's warning us that gravity is breaking down? And it's our first hint of that. So I quite like this analogy that I've given you on this slide. There is a sense in which it is actually a terrible analogy. And if you ask me at the end, I will tell you why it's a terrible analogy. Nevertheless, how might we modify gravity? So if we really want cosmic acceleration to be due to corrections to general relativity, so the philosophy here would be the universe has matter in it, baryons, dark matter, radiation, but nothing else. And acceleration is because the way in which space-time responds to that matter is not the way we thought on large scales. It's not because of general relativity, it's because of a different theory of gravity. And when you take that into account, you get acceleration. That's what we would like to ask that question. Is that possible? So one thing you want to understand is what degrees of freedom are there in your theory? And gravity is generally described by a metric. We could try to do away with that, but I don't actually know a way to do that. And so the first thing to ask as a particle physicist is, what degrees of freedom does the metric contain? Because I want to understand how do I go about constructing new theories? And here's the answer. The metric contains a spin 2 piece called a graviton. That's something we all know about. It's what we're familiar with in general relativity. It actually contains a couple of other kinds of particles that we don't talk about very much in GR. A vector field, spin 1, and scalar fields, spin 0 fields. And we don't talk about those when we talk about general relativity. And there's a very good reason for that, and that is that the equations of motion of general relativity, not the symmetries or anything like that, the equations of motion constrain those extra in principle degrees of freedom and pin them down and don't let them become dynamical fields. So the vector and the scalars are non-dynamical. The only dynamical degree of freedom that remains is the graviton, h mu nu. Okay. But it's also true that almost any other action for gravity that you chose to write down will not do this and will in general free up some of the new particles. Okay. And so that allows for all kinds of interesting things to happen, maybe relevant to cosmic acceleration. And in fact, things even more interesting than this are possible, such as massive gravity, that I'll mention a little later. So what are the propagating degrees of freedom? Well, which degrees of freedom, as I've mentioned, propagate depend on the action you write down. So in general relativity, the action is the Einstein-Hilbert action. You write down this simple functional of the Ricci scalar, and that's what gives you Einstein's equation, and that's what tells you that the only propagating degree of freedom is a graviton. The resulting equations of motion have constraints that do this for you, and they're very similar to Gauss's law. So I've said this already. Unfortunately, this got repeated. But if you try to go from Einstein-Hilbert to some new action, you're going to get new degrees of freedom. So here's an example. It's a very simple example that we wrote. I mean, other people have used in different contexts, and we wrote down a long time ago now with Michael Turner and Sean Carroll and Victor Davuri. Suppose you take the Einstein-Hilbert action, and instead of writing just the Ricci scalar, make a function of the Ricci scalar. Simple, pretty innocent thing to do. And if you do that, then it turns out that theories like this are very special. They free up only one of those new degrees of freedom, a scalar field. That's it. And it turns out that you can think of that degree of freedom as having a potential, and that potential is governed by the functional form f of r. And as you might imagine, that opens up the possibility of cosmologically interesting evolution. So it turns out actually that this gives us an entirely new class of actions, all of which can give you late-time cosmic acceleration. In fact, the equations of motion that you get in this theory are fourth order, and it allows you to reproduce any cosmological evolution you want by choosing the function f of r. In many ways, this is too much freedom. So it turns out you can fix the expansion history. The analog of the Friedmann equation in these models can be written this way, where this thing I'm calling rho effective contains all the extra gravitational interactions that new action writes down. And if you want that, if you want to know how to construct a model, if you hand me an action history that you want, that you've obtained through measuring the universe, maybe one that decelerates and goes through radiation domination, then matter domination, then accelerates, I can just tell you what class of choices of function f of r can give you that. So this is kind of designer f of r gravity. The problem with theories like this is that they're a disaster. Not always, but very frequently. And the disaster is not in their cosmology, which can have problems, but is generally not so bad. The problem is in other measurements of gravity. Okay, solar system constraints are order one wrong in theories like this, unless you have some very clever mechanism to make the solar system behave well. And I'll talk about those mechanisms in a little bit. That's a strong restriction on models. In fact, I won't even say that. In fact, I'd like to skip this slide as well. So I'll come back to these constraints in a moment, but let me just tell you about the other things that can happen. So you might say, well, okay, it's promising that we could get acceleration by modifying the action. It's a pity that things didn't obey the solar system constraints. Maybe there are more general actions that can do the job. And people have thought about that. We certainly thought about it. And so here's the most general thing you might imagine writing down. Some function of any number of scalar invariants that you can construct from a metric. Okay, so squares of the Riemann tensor, squares of the Ricci tensor, et cetera, et cetera. Unlike f of r models, it turns out in theories like this, it's really easy to satisfy solar system constraints. And the basic answer, this is a little too simplistic, but the basic reason is that in the solar system, very roughly speaking, the metric looks a lot like the Schwarzschild metric, and the Schwarzschild metric as r is 0. Whereas if you write down a general thing like this, then r mu nu rho sigma squared for the Schwarzschild metric is not 0, and therefore things look a lot like GR in the solar system. So that's great. You can satisfy these solar system constraints, and you can get accelerating solutions. So that seems like real progress. However, this comes at a terrible price. F of R models, while they have this problem with solar systems, they are what we would call ghost-free, except for some very special examples. But in more general models, like the one I wrote down, almost always one of the extra degrees of freedom turns out to be a ghost. And by a ghost, I mean something with negative kinetic energy. I'm going to say a lot more about that in a minute. These models turn out to be theoretically so sick that you just can't work with them. So I'll try to explain what those problems are in a little bit more detail. And they're problems that could arise in dark energy models or in modified gravity models. And to a particle physicist, the most natural way to think about these things is not as dark energy or modified gravity. It's in a common language, which is effective field theory. So the way we think about it is the following. It doesn't really matter what's causing the universe to accelerate. Ultimately, there is some background evolution of the universe. It consists of some interacting set of fields. One of them could be a metric, but other fields too. You have to write down a Lagrangian, and there are really only three types of terms that appear in Lagrangians. There are kinetic terms like this for scalars or vectors or fermions or anything really, and functions of them. There are self-interactions, or what you might think of as a potential. So interactions that of a field with itself. I've given you some examples here. And there are interactions among fields. For example, scalars interacting with fermions, vectors interacting with scalars, scalars interacting with other fields through the metric, et cetera, et cetera. Those are the only kind of types of interactions you can have. And depending on the background that you have, depending on that expansion history that you're interested in,
terms like this might have functions in front of them that depend on time and or space. And many of the concerns that theorists have about constructing sensible models can be expressed in this language. So here's an example, weak coupling. When we write down a classical theory described by a Lagrangian, usually we assume that the effects of higher order operators are small. We only have a finite sized piece of paper. We chose to write down some interactions in our theory. There are interactions we could have written down, but we didn't. The reason we don't is that they're typically higher order. As long as we work below the energy cutoff of the theory, we can ignore them. And self-consistently in that regime, quantum corrections will not regenerate those extra terms and screw up our predictions. To do that, you need all the dimensionless quantities that determine how those higher order operators come into the theory to be small. Okay? In other words, you need the energy of the phenomena you're considering to be less than the cutoff typically. But this is tricky. In a simple quantum field theory, expanded around Minkowski space, we understand this really well. But a theory is expanded around some expanding background, then it's very complicated. The kinetic terms and the couplings themselves and the potentials all can have background dependent functions in front of them. And even if all the original parameters you wrote down in your theory are small, it could be that expanded around some background, some of them get large. And then you have what's called a strong coupling problem. You just can't trust the theory. Okay. So just to give you an example, you could imagine a coupling between two fields, chi and phi, that looks like this. But if chi takes some time-dependent background along the expansion of the universe, that becomes a function of time times a kinetic term. And you could ask, what happens if that function goes to 0? And the answer is that's a strong coupling regime of the theory. You just can't trust the theory anymore. So it makes it quite complicated to seek theoretically well-behaved models. Another problem is technical naturalness. Okay, even if quantum mechanical corrections do not ruin your ability to trust a theory, you know, you've managed to always work below the cutoff of your theory, like I just described, you might need some really small couplings in your theory. Think of the very shallow potentials of dark energy that I mentioned earlier. So for example, using that model, suppose you need a really flat potential or a small mass. Most dark energy models, the simple ones, are scalar field models like this, where the mass is of order the inverse Hubble scale. Very, very tiny. The problem is that unless your theory has a special extra symmetry, as you take that mass to 0, then you'll just compute quantum corrections in this theory, and the quantum correction, the mass of your theory will receive corrections all the way up to the cutoff of your theory. Okay. And if you don't do this, then you have an extreme fine tuning to keep the potential flat, keep the mass scale low, and now you're back to a problem of technical naturalness, which is the problem you tried to solve in the first place by having dark energy. The things I've said so far, I think, are pretty typical things that you would encounter if you've ever seen a scalar field theory. The next two things are a little bit more technical, but they might be a little bit more for experts in the audience. One is this ghost-free thing I mentioned earlier. The kinetic terms in a Lagrangian, expanded around a background, tell you in some sense whether the particles associated with the theory carry positive or negative energy. So remember kinetic terms, right? So here's just some complicated example. Suppose I have two fields, chi and phi, and they couple in this way, some function of chi, some function of the kinetic term of phi. I'm sorry, that should say d mu phi, not d mu phi. And then you expand around some background, which depends on time and maybe space. And the effective kinetic terms for phi look like this, some function in front of phi dot squared and some other function in front of grad phi squared. This term here in front of phi dot squared sets the sign of the kinetic energy in your theory. If it goes negative, the theory has ghosts. That means that the particles of this field now have negative energy. And that can be catastrophic. If you take them seriously, ordinary particles could decay into heavy particles plus ghosts. So ordinary particles could not be stable. Or the vacuum itself, in fact, could just fragment into positive and negative excitations. Theories with ghosts are just sick, and you can't tolerate them. So you really have to be careful this doesn't happen to your theory if you're writing down the model. Just to give an example, here's an example which is very relevant to the most general functions of curvature invariance that I wrote down earlier. It's when you have uncontrolled higher derivatives in the theory. If any of you have taken classes, well, most of you will have taken classes in dynamical systems. In dynamical systems, there's this fact that if you include equations of motion that are higher than second order, in time, then you typically get what's called the Ostrogradsky instability, which is a classical instability of classical dynamical systems. In the quantum theory of fields, there's a similar effect, which leads to ghosts. So here I've got a theory of one field, psi. I've got a kinetic term, a potential, and I've introduced a higher derivative interaction, box psi squared with a cutoff. That seems pretty reasonable. Why would I not do that? But just to see that, suppose I define an auxiliary field, chi. So now I have a new Lagrangian, which looks different to my original Lagrangian, but note that chi here is just a Lagrange multiplier field. So it has equation of motion chi as box psi, essentially. And if you substituted that back in, you get my original Lagrangian. So this is, at least classically, an exactly equivalent theory. Now you make a field redefinition. Psi is phi minus chi. Integrate by parts in the action. It's simple to do. I'm just not going to do it here. And here's the Lagrangian that results. This Lagrangian is entirely equivalent to the first one I wrote down. And now it's a Lagrangian with two fields. One of them has a mass, and there's the potential. But notice that the kinetic terms are opposite signs. This is exactly the ghost problem. So in this model, I started off with one field. I just gave it a higher derivative interaction, ended up with two fields, and one of them was a ghost. This happens a lot, and it's something you have to be really careful of. This is why, to cut a long story short, within general relativity, almost any attempt to get a sensible model which gives you W less than -1 fails, because it typically has this kind of problem. There are other problems, such as superluminality. This and the next slide are really for aficionados, I would say. If you write down a Lorentz invariant quantum field theory, one crucial ingredient is microcausality. You have two local operators, they vanish, then their commutator vanishes at space-like separated points. This is just a statement that nothing travels faster than the speed of light. But it can turn out that even if you have a well-behaved theory, you can ruin this in theories like this. And that's because the causal structure is not set by just a half d phi squared. It's in principle set by some function of other fields in the theory, or background fields, and that can ruin the causal structure. And I'm not going to say anything else about that, actually. In fact, I'm going to skip this slide because I think it's too technical, but I can come back if you ask me questions about it later. Sorry. Okay. Now, one thing the effective field theory is very useful for is understanding what kinds of physics you need to be consistent with observations, and in particular, the need for screening. So suppose I have a scalar field that's conformally coupled to matter, and I've written down some general Lagrangian. So imagine I've got, say, some scalar with a kinetic term, but which has a function in front of it, has a potential, and then I just couple to the trace of the energy momentum tensor of matter, because that's a simple lowest order interaction between matter, between phi and other matter. Now specialize to a point source. Think of the sun, okay? So that the trace of the energy momentum tensor of the sun is really just a point mass localized at the origin, and expand around a solution phi bar. So if you do, so I'm going to put that source in, I'm going to solve for phi, call the solution phi bar, and then look at fluctuations around it. You get a wave equation that looks like this. And this looks very complicated, but it's actually quite simple, okay? All I really need to focus on here is that if the background of the field, phi bar, is set by, the local density or the Newtonian potential or something like that, then if I can neglect spatial variation, this equation is simply solved, and it just gives me an interaction with a potential that looks like this. And we recognize, all of us should recognize parts of this potential, even though it looks complicated, okay? Sorry. It has a couple of different pieces. It has a 1/r piece. 1/r is a Coulomb potential, and so that's something we're used to thinking of. But it also has this e to the minus mr piece, and that's a little bit like a Yukawa potential. Okay, and that's the only things I really need you to pay attention to here. The problem is that if you have a light scalar, m of phi bar here is low, small, then that Yukawa potential is not very important. This really is a Coulomb potential. That means that point masses in a background like this not only feel the gravitational Coulomb potential, they feel a Coulomb potential due to this new scalar I've introduced. And it's an order 1 correction to the gravitational effects. But general relativity, if you like, even Newton's theory, but general relativity is tested remarkably well in the solar system, 1 part in 10 to the 5. And so an order 1 correction, we would know. And it's not there. And so this, in the language of effective field theory, is exactly the problem I mentioned for F of R gravity. You will ruin the predictions of gravity in the solar system by introducing new fields unless you are very careful. And very careful here means something very specific. You need a way for those fields to very dramatically modify general relativity on large scales so that they accelerate the universe and be essentially irrelevant where we test general relativity well, solar system, and increasingly in galaxies. How do you do that? Well, the way to do that is through screening mechanisms. Let's go back to the effective field theory classification in terms of what appears in the Lagrangian. Remember, there are 3 kinds of terms. Along with those 3 kinds of terms, there are 3 ways to implement screening. One of these is called the Weinstein mechanism. That's going to use the kinetic terms that I wrote down, and I'll explain how it does that in quite a bit of detail in a moment. Another way is through what's called a chameleon mechanism. That uses the couplings between matter and a new scalar to shield, to change the dynamics of the scalar in the solar system, for example, in such a way that it doesn't modify gravity very much there. And there's a third method that uses self-interactions to do the same thing. I won't have a lot of time in this talk, so here I will really mostly focus on the Weinstein mechanism, partly because I think it's the most interesting. Now, the reason I think it's the most interesting, so I am going to tell you about the Weinstein mechanism in some detail. Before I do that, though, let me just say why I think it's the most interesting. It's the most interesting because it's relevant to what I think has been one of the most exciting ideas in terms of how to modify gravity of the last decade or so, and that's the idea of massive gravity. Okay, so, gravity, when we talk about the graviton being massless, what do we mean? We mean that if we take the Einstein-Hilbert action and we expand it out, you see the spin 2 piece that I told you existed, and it does not come equipped with a mass term. So from a particle physics point of view, the quantum field theory that describes gravity around some background is that of a free spin 2 field with no self-interactions, including no mass, and other than self-interaction corrections, and therefore it's massless and propagates at the speed of light. But you could ask the question, well, if I go away from GR, what about that? Could I give gravity a mass? And in fact, a long time ago, Fierz and Pauli showed how to do this in a very similar way, a linearized version, okay? That means you just write down a kinetic term for a graviton, h, and you choose a mass term that's a very particular combination of the trace of h and h mu nu, h mu nu. If you do that, then it turns out that at the linearized level, you have a perfectly well-defined massive theory of gravity. If you don't choose this mass term, you get a ghost. But when we know we don't like ghosts. But if you choose this mass term, you don't get ghosts at the linear level. But in the 70s, it was shown fairly comprehensively by Boulware and Deser that even this doesn't help you because they thought that they showed that essentially, in fact, they thought all nonlinear completions of this theory. In other words, if I want to write down an action like I do for general relativity, but an action for massive gravity that linearizes to this form, anything of that kind would resurrect this ghost, and you'd have a negative energy degree of freedom. The theory will be nonsensical. And the remarkable advance of the last decade or so has been that a counterexample, or in fact a class of counterexamples to this has been found. Okay, so this goes back to the work of Daram and Gabadadze, and then Daram, Gabadadze, and Tolle a decade or more ago, where they showed that, and I won't be providing details of this, this is just to guide the eye, that it is a very clever way of writing down mass terms for the graviton. So here I've sort of schematically written down the Einstein-Hilbert term in the Lagrangian that we know exists for gravity, and then sort of a potential for gravity. And they showed that there's a clever way to introduce something called F, which is a fictitious metric. And by doing that, you can find a very, very clever selection of interaction terms such that you just thread a very careful line in massive gravity and eliminate the Boulware-Deser ghost and have a perfectly well-behaved theory of massive gravity. So that is ghost-free. And people have been working on this for a decade now to understand its cosmological implications. People are very interested in this partly because when you have something with a mass, then it doesn't have an infinite range. Therefore, you might wonder, if I'm thinking about the accelerating universe, maybe this is an example of a field where on large scales it modifies gravity, order 1, massless field, but locally it doesn't because it has a mass or something like that. And we'll see in a minute that to some extent that's true. But I won't study massive gravity in this talk because it's too much work for a small talk. What I'm going to do instead is point out that both for entirely other reasons, other types of theories, but also because it appears in a particular limit of massive gravity, there is a theory, a scalar field theory called Galileans, which exhibits many of the features of massive gravity and is much easier to describe. So I'm going to use that for now. So what are Galileans? So now I just want to focus on a new class of scalar field theories that has very bizarre behavior and might be very useful for understanding the accelerating universe, and is going to show you precisely how this screening effect, this Feinstein screening, works. So I want you to imagine I am looking for a scalar field theory. I'm going to call the scalar pi for sort of historical reasons, and I can explain why later if people like. And it has a particular symmetry. The Lagrangian the action I want to be invariant under pi goes to pi plus a constant, well, that's a simple symmetry, plus b mu x mu. One way to think about this is that it's two symmetries. Pi is invariant under shifts in pi. Pi goes to pi plus c. And then if you imagine differentiating this expression I wrote down there, then you would have d mu pi, or d nu pi, let's say, goes to d nu pi plus b mu, b nu. And so what you're saying is that this theory is invariant under shifts of the field and linear shifts of, if you like, the velocity of the field. That's why they're called Galileans. It's just a linear shift in velocity of the field. So you could ask, in the effective field theory, what kinds of things can I write down that are invariant under this symmetry? And it turns out it's a relatively small number of things. Obviously, any term you write down with two derivatives acting on the field is always invariant under this. So those are not very important. What's really important are special terms like these. You can have pi, a tadpole term. We won't worry about that because you can redefine tadpoles away. Kinetic terms themselves are also invariant. This higher derivative looking term is invariant. And in fact, there are a lot of other terms you could write down in general dimensions that look like this. In theories like this, I should say in 4 dimensions, however, there are only 5 terms you can write down. Theories like this, there's a remarkable separation of scales that I'm about to show you. What it'll allow us to do is have classical field configurations in the theory with order 1 nonlinearities. So those nonlinearities are going to be very useful for addressing agreement with tests of gravity in the solar system, but within which quantum effects are entirely under control. So you can study nonlinear classical solutions. I'm going to show you that we get screening. And we now understand there are many, many variations on this structure, which I won't have time to talk about today. Okay, Galileans take this form, okay, where you, the tensors antisymmetric in mu indices, antisymmetric in u indices, symmetric under exchange of any pair. Don't worry about that. As I said, there are only n of them, non-trivial in n dimensions. And for us, that means there are actually 5 in general, but one of them will be the tadpole, so really only 4, which is right around. I'm going to ignore this thing because I have time constraints. Okay, let's see how the Feinstein effect works here. So remember the point in case we're losing it. I'm introducing a new scalar field into the theory with, in principle, gravitational strength interactions. And I want to argue that that changes gravity on large scales, but I want to argue that it does something very clever not to change gravity on small scales so that everything we know about the solar system remains unchanged. So let's take one example. This is, all I've chosen is one of those Galilean terms. I've got a kinetic term, which I've given a weird normalization just for convenience. Don't worry about that, -3. And then this weird higher derivative looking term, d pi squared box pi, and again, a couple pi to the trace of the n-dimensional tensor of matter, like I did when I showed you the problem that we needed screening. Now let's again look at spherical solutions around a point mass like we did earlier. And you find a remarkable fact. The background solution for pi has two asymptotic behaviors. If you're very far away from the object, right, so this is an object of mass m, so if you're very far away, I've defined something called the Weinstein radius RV. If you're much further away than that, you just have a Coulomb potential. So what that would mean is that this would provide an order 1 correction to general relativity at very large scales. But on small scales, much less than this Weinstein radius, the field has a different profile. And that different profile means that if you look at a test particle and compare the strength of the force due to pi to the strength of the force due to gravity, or Newton's law, if you like, then again, as I just said, on large scales, that's an order 1 correction. On small scales, it's very suppressed by this power of distance over the Weinstein radius. So forces are much smaller than the gravitational strength within the Weinstein radius, and that means they're safe from fifth force tests. That's difficult to say. I'm going to skip this part until later. What that means is Galileans are a very unusual type of scalar theory, and so is massive gravity, by the way. Usually when I give you a quantum field theory, there are sort of two regimes. One of those regimes is what we might call the ultraviolet. It's very short distances. Here I'm showing it very close to the source. Distances much less than 1 over the cutoff. Classical nonlinearities there can be much bigger than 1, but more importantly, quantum nonlinearities are much bigger than 1. And typically we do not know how to compute what happens in a theory in that regime, okay? The other regime, so that's the usual quantum, highly quantum regime of the theory. The other regime is what we normally call the usual linear classical regime of the theory, or perturbative quantum regime. You're very far away, you're in the IR of the theory. Classical nonlinearities are small, quantum corrections are small, and you can just compute things in a well-defined way. What's different about Galileans is that there is a third parametrically large region between the inverse cutoff scale and the Weinstein radius, where quantum corrections remain small. So you can completely control things in a classical way, but classical nonlinearities can be big. And that means you can use those classical nonlinearities in a theoretically well-defined way to, for example, screen fields and have them not screw up solar system tests of gravity. So this is a new classical regime with order 1 nonlinearities. That's what makes these things special. For the experts among you, these theories come equipped with all kinds of wonderful properties. They are non-renormalized. You can expand their quantum action out and show that they do not receive quantum corrections to any order in perturbation theory. So they're very protected. And remember, I told you that's something that theories really like to have earlier in order to remain technically natural. I won't harp on these slides. I just want to flash them by. And for the real aficionados and mathematical fans amongst you, there's a very nice mathematical theory that goes along with Galileans, which allows you to construct them as Wess-Zumino terms and describe them, their existence through non-trivial cocycles in Lie algebra cohomology. And we have a long paper about that, but I won't talk more about it in this talk. I want to tell you that this Weinstein effect is very, very effective. Okay, for example, if you choose your theory to give you cosmic acceleration, then the Weinstein radius around the sun is 10 to the 7 astronomical units. So you're very safe, and there are similar measures for galaxies and clusters. Okay. But the cosmology is quite tricky, and I see I'm coming to the end of my time, so I want to actually skip through these slides and just say one last thing about testing it. So what the goal is going to be going forward to take theories like the ones I've described. I focused a lot on their technical naturalness, but the goal will be to go out in cosmology and now try to test them in a variety of ways. The way to do that is to fix the expansion history of the universe to be the accelerating one we know exists, and then to test the way in which matter clusters on different scales and use that to distinguish between these modifications of gravity that I'm talking about and general relativity. Okay? In other words, gravity does two things for you. It drives the acceleration of the universe, but also governs how matter clumps up. And those don't have to be the same in different theories. And that might help has to distinguish a cosmological constant from dark energy, from modified gravity, from massive gravity, et cetera, et cetera. Okay. There's a lot of work remaining to be done here. And I'm definitely going to skip this slide because I'm running out of time. And I think we now have new tools, I should say. Many of these theories are getting constrained by gravitational waves. What I want to do is just say these theories are very difficult. What I've tried to lay out is the criteria that must be satisfied by these theories. Currently, there's no satisfactory understanding of acceleration. There's a lot more work needed. Screening is a very powerful effect, and it's really needed to make these theories consistent with solar system effects. But screening is actually quite poorly understood. We know how it behaves around static sources, but if we really want to test these theories in the solar system, we want to understand how screening works around highly time-dependent sources. A lot of work remains to be done there. And you might worry about the UV behavior of these theories, and that's something the theorists spend time doing. So just to summarize, since I've hit, I think, the half-hour mark, the 9:30 mark, cosmic acceleration is a very deep problem. We're very fortunate that data continues to flood in and will continue to flood in to help us try to get to the root of it. But the theoretical side faces some serious questions, even if a cosmological constant is the right answer. And a lot of us are hard at work on this using insights from cosmology, gravitation, and particle physics. And I think we're quite far from a solution, to be honest. Many ideas are getting ruled out or tightly constrained by data from completely new tools, such as gravitational waves, LIGO, and etc. And one thing I wanted to really hammer home here is that thinking about the theory of this is that serious models only need apply these days. Theoretical consistency, ghost freeness, good behavior in the UV where you can compute it, technical naturalness, etc., are crucial. And if you don't have them in your theory or you can't ask those questions, the theory is not really a contender these days. I think I'm going to stop there because of time, and thank you and open up to questions.
Thank you, sir, for your interesting and illuminating talk. It is a very nice topic in cosmology. So to the participants, if there is any question or query.
Yes, sir. Can I proceed, sir?
Yes.
Yes. Thank you, Professor Mark, for this very interesting talk. And this topic is so interesting for me. And I'm also a newly joined PhD student in this topic also. So my question is that you have introduced that the field that will be in quintessence theory that should be coupled with the dark energy in the Lagrangian prescription. So if I have any prescription to quantize that field, so can I get a mediator of dark energy?
Yeah, so certainly, indeed, the phi that I wrote down is a quantum field. It's a legitimate quantum field. You should, in fact, quantize it. You have no option but to quantize it, and it will mediate interactions with other fields. But if you want it to be consistent, not only be consistent with everything we observe, but also to behave well as dark energy, it better not interact very strongly with other fields. And because of that, that's one of the things I was kind of implying when I said that you need to keep artificially small values of the couplings. And so we do not expect at all, for example, to observe interactions of quanta of dark energy in colliders or anywhere else, if that's helpful.
Yes, I got it. And another question, you have introduced also the modified theory of gravity here. It's especially f of r theory of gravity. But in the context of dark energy, it's my experience is very small. So I am in the phase of literature survey. I have seen that in the late time universe they have only taken f of r equals to some r. So my question is, if f of r equals to r in the late time, so why I am introducing the modified f of r in this case?
So you will need, you cannot have, if at late times you have lambda plus r, then you're not solving cosmic acceleration with f of r gravity. You need to have something else. Now, it's true that there are constraints that one has on these theories, such that the form has to lie in some pretty tightly constrained region. But you certainly are allowed to have deviations from that at the level that you can test it in structure formation. So what I would say is that it's not just R, it's other things too. But most
so you mean to say R plus something nonlinear R square, something like that, or
other things. But
Okay,
what I really
okay.
want to say is, most importantly, if you have that, then the effect of that is not just today, but it imprints itself on through fluctuations on the on structure formation. And so in principle, one can probe that by measuring structure formation, even if late time acceleration is very similar to that due to a cosmological constant.
May I ask one thing, Mark? You see,
Yes.
you mentioned about the gravitational waves. So I was
Yeah.
wondering, with regard to the modified gravity like FR or something, the modified gravity like FR will give rise to the scalar degree of freedom, and there would be the scalar modes in the gravitational waves. Don't you think that that could be used as a mark of distinction between the modified gravity models and the lambda CDM models? I mean, we can have this as a constraint. We can use it as a constraint, and maybe the observations will be the final thing to decide upon it. If we have that kind of, if you have a massive scalar degree of freedom that gives rise to the scalar modes that propagate with different speeds, at different speed, right? So they would show some kind of a dispersive nature as well, right? So
Yeah.
what kind of do you agree that if we are able to nail down this issue in some better detections in the gravitational wave experiments probably, or observations, then that could be used probably as a tool to distinguish between the modified gravity models and the lambda CDM models.
Most certainly. I mean, so I skipped through it rather quickly, but so it's a complicated question, but the short answer is yes. I mean, I think it's exciting. So to give one very concrete example, people sometimes, I'm not a big fan of this, but people sometimes like to write down the most general scalar tensor theory that is consistent with second order equations of motion. So we could have a long discussion about how that people should think about that, but let's not worry about that. Sometimes they call these things Hondesky theories. So people have written those down, and then there are many, many interactions in these theories, and one can tune them and get acceleration, et cetera, et cetera. The very first observation that was made in 2017 of simultaneous observation, an observation where LIGO got a measurement and simultaneously you got an optical counterpart. The fact that you could measure both those things, and that gave you a comparison between, for example, speeds, killed a large swath of approaches to dark energy from those models. So that alone, exactly in the way you're describing, was incredibly effective. It's
okay. You go ahead, please.
Yeah, so that's great. So yeah, I completely agree. The complications are there are two complications. One is massive gravity. It's not a big constraint on massive gravity right now because the mass is so small that it's not tightly constrained by this. I mean, people have written papers on this. I'm just saying it's not ruling it out or anything. The other thing is, everything I've said so far is to do with how gravitational waves propagate, as you said, like whether you can radiate into some scalar mode and they propagate. How they radiate is a much more complicated problem, right? As so you might think that if I had two massive bodies, say doing an orbit, then they would have a screened radius around them. And that would mean that they would behave very much like general relativity. And even if there was some new degree of freedom, you could not radiate into it because you're in the regime where you're screened.
Yeah.
But it's not completely obvious that that's the case. And people have written papers about it. I've written a paper about it. Other people have written papers about it. And it's possible under some circumstances that you could radiate into this other modes. And indeed, you could constrain theories that way. But it turns out to be a really hard calculation. So I think there is possibility there for real progress. Yeah.
Yeah. And I was also wondering about say, making a distinction between the theories, I was wondering whether we could use the perturbative solutions of the binary systems in order to make a distinction between lambda CDM and these kind of FR or some other models. Right?
I think for things like FR, it's easy to do, but for other ones, it's much harder. Yeah. Yeah. I mean, I think you're asking again about generating, basically.
Okay. Yeah. Yes.
And what makes it hard, I mean, you're not wrong. Of course, that is the natural thing to try. I don't disagree.
Right.
What makes it difficult is this whole screening thing. I mean, in general relativity or in quantum field theories, in simple quantum field theories, the background solution does not introduce new scales into the problem typically. But in these theories with their very weird self-interactions, as the background solution evolves, it feeds back very strongly into the functions that appear in the equation of motion for perturbations. So it's a very difficult problem, I think.
Yeah. So that is what I was wondering. The exact solutions are more or less the same, but then the perturbations might be used as some kind of diagnostics or something in order to.
Yeah, I think that's right. Yes.
Thank you, Mark.
Sure. Thank you.
Any other question?
Sorry, sir. It's not a question, but it's a request for Professor Mark. Sir, if I drop you a mail for requesting your slides, can you please provide the slides today? It will be helpful for my session. Thank you. Thank you. Sir.
So if there is no other question, let us thank Professor Mark Jordan for introducing us a very new topic in gravitation and cosmology. And I express my sincere thanks for giving his nice talk at ICART, North Bengal University. Because of pandemic, we are bound to do this. In future, I hope that we will somehow physically meet either in India or outside. So till then,
I would like that too. Thank you.
Thank you.
Yeah. Thank you, everyone. Thank you for the invitation.
Thank you.
It was very nice to be there.
Thank you, sir. So it is now concluding part in this one-day seminar on astrophysics and cosmology. There were four notable speakers. Professor Kanak Shah from IUCAA, India. Also, we can tell that he is from North Bengal. He is with us. Then Professor K.K. Nandi, who is now in Russia. Then Professor Dipankar Bhattacharya from IUCAA, and Professor Mark Troden from Pennsylvania, United States. We are very much thankful for their precious time to spend with us in these invited talks. We are also thankful to Professor M.M. Bharma from Lucknow University, who kindly agreed to chair and successfully chaired all the sessions. And the participants, basically the students, research scholars, and the faculties of different universities and institutes, not only in India but outside, they have participated in this seminar and asked questions. There was an interactive session. So I hope that it will be beneficial for all of us. So I thank you again for all the participants and the research scholars of this department who has taken care of arranging this seminar smoothly. Thank you. We hope to meet you again in some other platform. Thanks. Bye-bye.
Bye, sir. Bye.